So here's the science behind what we're doing today. It's all about elastic force. Elasticity is a property of solid materials, like this elastic, and how much they tend to return to their original shape when deformed, like when I pull on it. Elastics are called elastics because they're great at doing just that. You can pull on it and pull on it and pull on it, and it'll, always return to its original shape. So we are using the power of elastic force today. Ow.
Now it's time for a Science Max quiz. Elasticity is the ability for a material to return to its original shape when deformed, like this or this. Which of these materials have elasticity? A rubber band, a pencil, or a rock? Haha! This is a trick question. The answer is all three. Most solid materials have elasticity. Nearly everything will deform a little and still be able to return to its original shape. It all depends on how much. This is a steel bar. This is an elastic band. And this is an ice cream sundae. We're not talking about ice cream sundaes now, though. So get that out of here. Good. Now, a steel bar and an elastic band both have elasticity. A steel bar can be stretched to 1% of its length and still spring back. A rubber band can be stretched 300% or more. The difference between the two is why we make balls out of rubber and buildings out of steel, because the other way around wouldn't be good for balls or buildings. This has been a Science Max quiz.
All right, let's build our catapult. The first step, take 4 pencils and stick your popsicle stick in between so you have 2 on the top and 2 on the bottom. And then use your elastic to go around and around and around. That's why I like building things with elastics, because it makes it very fast to tie things together, because once you go around and you have it nice and tight, you just pop it over the end and voila, it stays together. And that is how you start making your frame. Put more pencils on that side.
And another popsicle stick on the other end, held on at the corners with more elastics. Then, take even more elastics and put them right around the middle until you get this.
I've added a few more elastics around the middle here, and that is where we're gonna get all of our elastic force. I think I have 6. The more you use, the better it's going to work. Take your popsicle stick, stick it in between the elastics, and then start spinning it around. Here's the reason I use pencils and popsicle sticks, is because the pencils are a little bit longer, which allows you to twist the popsicle stick around in the middle and build up the elastic force. Now, because I'm twisting, the elastic force we're using here is called torsion, or twisting force. When you feel you have enough torsion, pull your popsicle stick down a little bit so it won't unwind on you, and you'll see that you have all kinds of elastic energy. Then, take your spoon and stick it on the popsicle stick, and you can also break off the popsicle stick if you want to make sure it's the right length. And it works like that. To make the frame, you just need more pencils and elastics. The trick is to make a triangle with 2 pencils attached to your frame. They should stick up right where your catapult arm would be fully upright. Then, take a final pencil and put it across the top. Don't forget to pull the arm back before you put the pencil across, otherwise it'll end up on the wrong side. Now, this is very complicated and I went pretty fast, so if you want the step-by-step instructions on exactly how to build this, go to our website. And there you go, a catapult of your very own that you can use to knock down very small castle walls. I've also built a larger catapult using all of the same principles. Pretty good, huh? It's got a longer arm, which means I can throw marshmallows even further. Whoa. Or I can throw larger marshmallows, or I can throw very large marshmallows. Whoa. Now, I know what you're thinking. You're thinking, Phil, is that the largest catapult you're gonna make? Well, of course not. This is Science Max, experiments at large. I'm headed to the Center for Skills Development and Training, and we're gonna max out the catapult so that it's big enough to throw one of these. Zach.
Hey, Phil.
How you doing?
All right.
This is Zach. He's a mechanical engineer, and you build machines for a living, right?
That's right.
Great, because I need help building a catapult.
Okay, but what's with the pumpkin?
Now, the pumpkin is what I want to throw out of the catapult. See, I figure we just take the small design and we just make it so that we can throw one of these. What do you think?
You're gonna need a really big catapult.
Yeah, and I'm also gonna need some really big elastics. Where do you get those?
Well, in medieval times, they used rope to make large catapults.
Oh, okay, well, rope is a lot easier to get, and that would be fine. And I want to make this arm as long as this piece of wood here.
This is gonna be a huge catapult.
It's a huge catapult. I guess we should build it outside, though, huh?
Let's do it.
Okay, it's over that way.
Okay.
I'll follow you.
Sure, do you want a hand with that?
No, I'm fine. You go ahead, and
Okay.
I'll just, maybe if you hold the door open for me, I could just hold, no, you know what, you go and I'll meet you.
You sure you're good?
Our full-size catapult is going to look a lot like the popsicle stick version. We start with a 4-sided frame and add some legs on the bottom. Our spoon is going to be replaced by a long throwing arm with a basket on the end. Then we need a really strong cross brace at the top to stop the arm. Just like in the small version, using a triangle shape is the best because triangles are very strong. Finally, we need something to wind around and around, which is going to give us our elastic force. Instead of elastics, we're going to be using rope for our catapult because rope has just the right amount of elasticity. But unlike medieval times, we're going to be catapulting pumpkins. Once Zach and I got it all put together, it looked like this. Okay, we have built a catapult. Check it out. It's pretty solid, and I think it's pretty amazing. And just like in the small catapult, we have our elastic force. But this time we're using rope, right, Zach?
Yes.
Okay, and rope will work as well as the elastic did in the small one?
Yeah.
All right, great. So what do? It's really loose now.
We need to wind this up so that we put some tension into it.
Go!
The reason a catapult works is because the rope is twisted. The elasticity in the rope wants to unwind, which gives the catapult its power. Just like the small catapult, the more you wind it, the better it works.
Good. Usually in medieval days, they had whole teams of people doing this job. But it's just me and Zach now. How you doing, Zach? All right. Okay. And then we clamp it on here. So the thing doesn't unwind, right?
Yeah.
Good. All right. Now we have our pumpkin, and we're gonna fire our pumpkin in our castle wall, which is made out of cardboard boxes over there. Pumpkin. All right, here we go. Pulling the arm back. Oh, that elastic force is pretty strong. Okay. How do you think that pumpkin's a good size?
Oh, it's pretty big.
You think?
Oh, a little too big.
It's too big for our basket. Smaller pumpkin! Smaller pumpkin! I'll hold this. No rush, Zach. No rush. Okay, rush, Zach. Can't hold.
Oh, yeah.
Can't hold arm. Okay, ready? 1, 2, 3! It didn't work that well.
No, not quite that well.
Yeah, so
Let's see.
it went and it flew and it landed here, which is a little farther away from the wall than I'd like it to be. 1/3 of the way to the wall! I don't know if that's enough. What do we do to make it better?
Well, the way we're throwing it right now, we just have the pumpkin in at the end of the arm. But
Yeah.
if we make some kind of a sling so that we fling it as we're bringing it up.
We make a sling?
Yes.
All right, I don't know how to make a sling, but you know how?
Sure.
All right, we'll make it and then you can explain how it works.
Yeah.
All right, good. Let's put the pumpkin over here. We'll recycle it later.
Max Historica.
Good morrow to you. I am Lord Fillington III, and welcome to my medieval castle. Throughout history, lords and kings have built castles and walls to keep people out. I built my castle to protect my prize collection of snow globes. I have so very many, and they're all mine. Ha ha! Oh, hello! You down there! You can't come in. This is my castle.
And throughout history, there have been people who've been wanting to get into those castles because Lord Fillington has been hogging all the snow globes, and I'd like to look at them. But the hard part is figuring out how to get into the castle, because I can't just come up to the wall and start hammering on it.
taste the wrath of my water balloon!
Because if I get too close to the castle, he can get me. Ha 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 ha! Fortunately, there's this thing called a catapult. Oh, fiddlesticks. They have a catapult. What you do is you put something heavy in the end here, and the catapult fires it at the walls of the castle, knocks them down, all from far enough away that the people in the castle can't get to you. Ah! Oh, I surrender! Don't knock my walls down! It'll take me all week to fix them. Oh. All right, you can have a snow globe. Oh. And that's how catapults were used in history. Oh, so beautiful.
Back to our maxed out catapult. Our first design threw a pumpkin just like it was supposed to, except it only threw it 1/3 of the way to the wall. Now Zach and I are planning to outfit the catapult with a sling. The sling attaches to the end of the throwing arm and gives the pumpkin a lot more distance to travel. Because the pumpkin is traveling a longer distance in the same amount of time, it will be going faster, which will hopefully get it to the wall, or at least a lot farther than before.
So we built this sling. How does this work, Zach?
Well, we've got one end tied here.
Yeah.
And then we put the pumpkin in here.
Wait. Okay, pulling arm down. Pulling arm down. Okay, yeah, now what?
Now we put the pumpkin in here.
Put the pumpkin in there.
Yeah. And then we loop this over the back of the,
Oh.
over that. As the throwing arm goes up, this will slide off the back of the throwing arm and it'll release the pumpkin.
All right, you're the expert. I believe you. Let's try it out. 3, 2, 1. Oh. Whoa. Okay. That
Better.
works really well. You know what the problem is, though? We still don't have enough oomph.
Yeah, it needs more power.
So what do we do? I don't know if we can crank that rope anymore.
I think we're at the limit of our rope power, but if we added some more elastic,
I thought we weren't going to use elastic.
well, we used elastics in our small demo models. What if we use some more?
We have elastics? I don't know
Yeah,
if
I
we
brought
have...
some in here just in case.
What's this?
It's surgical tubing.
It's like a giant elastic.
Mm-hmm.
Well, I guess this is elastic force. So do we twist
here
it
we-
around at the bottom there?
Well, we
or-
just wrap it around the throwing arm like this. And,
Oh, I see. So we tie
Yeah.
it here,
yeah, we just need a lot more, and then
we pull this, and it would be. Oh, yeah, that would
Yeah.
make a lot more. So we just need a lot more of this elastic. What is this again?
surgical tubing.
Surgical tubing. It's like a giant elastic. Fantastic. All right.
Goggles on.
Goggles on. Yes. Yes.
Here's another fun way you can play with elastic force. Take a milk carton. I prefer Science Max milk because it's the creamiest. 2% cream, 100% science. Wrap some elastic bands around it with some popsicle sticks on the bottom, sort of like feet. Then take some clamshell packaging, which wraps just about anything you buy nowadays, and cut out a square or a rectangle. Then wrap some tape around that square with an elastic in it, and put the elastic on the feet of your milk carton. Then wind it around and make sure you go backwards so your paddle wheel boat will go forwards when you put it in the water. And there you go, a paddle wheel boat. Now it is time to max it out. Ahoy, the SS maxed out elastic force paddle wheel boat mattress. I need a better name. But I've made a giant paddle wheel boat that will work on elastic force because I've got surgical tubing as my elastics, and that's an air mattress. And then I use some lumber to hold it all together. And of course I need a paddle wheel, and what better thing to use in a pool than a flutterboard. Okay, here we go. So normally you're not allowed to wear your clothes and your shoes in the pool, but I got special permission because of science. Besides, I'm not worried at all, so I didn't wear my swimming outfit because I figure I can totally do this entire experiment without even getting wet. That is how confident I am. All right, now the tricky part we'll be getting onto the mattress. Okay, here we go. Ha-ha! Whoa. Ha-ha! The SS Science! Hey, SS Science, that's a great name for this. Look, it works great, and I managed to stay totally dry. Huh? Well, almost. Whoa, oh, oh. Haha, you thought I was gonna fall in the pool, but I didn't. Uh-oh. My flutterboard has stopped moving, and I'm in the middle of the pool. Almost. Yeah. Didn't think this through. No. 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 No, that's not going to work. Maybe I'll wait. Our maxed out catapult was working well with the sling we attached to it, but it still didn't make it all the way to the wall. Zach's idea is to attach a bunch of surgical tubing to the cross piece of the catapult. Surgical tubing is pretty much big elastics, so we'll have two places we're getting elastic force from, the rope and the surgical tubing. Hopefully this design is enough to help our catapult fling a pumpkin far enough to hit the castle wall. All right, here we go. You hold that, I get this. We got our system down now. Okay. Oh. This goes up to there. Okay. Okay. 3, 2, 1. Nope. One, 2, 3. Oh! It went too far. It went too far. That's so good. Oh man. Right. Okay, so all we gotta do is move the catapult back. So you get that side, I'll get this side, and we'll move the catapult. See, now our catapult is too good. We gotta back it away from the castle. All right, let's go again. Aha, pumpkin.
Pumpkin.
Pulling arm back.
Pulling arm back. Grunting.
Loading. Pumpkin. Hooking rope on arm.
Hooking rope on arm. More grunting.
More grunting. Pulling back strongly. 1, 2, 3. Oh. Oh. Oh, wow. Woo.
We're inside the castle.
We're still inside the castle. Oh, man. It's an excellent shot, though. So what do we do? Move the catapult back?
Yeah.
Move the catapult back. What about
here?
Here. Here we go again. Pumpkin.
Pumpkin.
Loading arm.
Loading arm.
All right, you ready? You think it's gonna work? We've done every modification we can possibly do. So you think it's gonna work this time?
We did it. It's gonna work.
Okay, here we go. I'm excited. All right, ready?
Ready.
1, 2, 3. Whoa! Yeah! Woohoo! High fives! Well, there you have it. Awesome job. Now we need to throw fingers to see who gets to rebuild the castle. Okay? 1, 2, 3. Oh, thanks very much for joining us. Let's take a break. I'll rebuild the castle. You see, this is exactly how catapults used to work. They'd hit the same part of the wall over and over until they made a big hole, and that would weaken the wall. Fortunately for me, it's really easy to fix. Just put this right in here. Oh, man. Moving air is a lot of fun, especially if you use one of these, a vortex cannon. They're pretty impressive and they use some pretty amazing science. I'll show you how to build one. It's pretty simple. All you need is a plastic cup, you want a balloon, something round, an elastic, scissors or a craft knife, and a pen. Here's what you do. Take your balloon and cut it just where it gets wide. You take the mouth of the cup right there, and you have to stretch the balloon over the top
And then you want to put an elastic around it, keep it in place. And this now is a surface on the top, and that's what you're going to use to pull back and create your burst of air. But of course, the air's not going to go anywhere until you make a hole in the bottom. So here's what you do. You take your round thing and draw a circle, and take your craft knife or scissors and an adult and get them to help you cut out a hole. And when you pull back on the balloon, a burst of air comes through the hole, but the air has an interesting shape. Now, I know what you're thinking. You're thinking, Phil, air is invisible. You can't tell what shape it is. Well, I can show you. Come on. This is my maxed out vortex cannon. It's made out of a garbage can. I've got a hole in here, and this is a shower curtain with a ball that I can get a grip on and pull, and then it shoots forward like this. Now, it makes a big puff of air, but again, the air is invisible, so we don't know what shape it is, but I can help with that because I've got this, a fog machine. I fill the inside of the garbage can so we can see what the air is doing when I fire the vortex cannon. Okay, come on over here. Ready? Whoa! Okay, ready? Check it out. The vortex cannon shapes the air into a ring called a vortex. It makes a ring, well, actually sort of a donut. Because of its shape, the air in a vortex can move much farther than air that doesn't have a shape. Vortex cannon. Air that has a shape goes a lot further than air that doesn't have a shape. And it's also way more fun. Woohoo! This is a climbing frog. Why does he climb? Because of science. I pull on this rope, and then I pull on that rope, and I pull on that rope, and he climbs up the ropes. And why? Well, because of friction. The secret is 2 straws. The straws are pointed away from each other at the bottom. This allows it to climb thanks to friction. Take a closer look. When I pull on one string, it pulls straight, which makes the frog pivot. That string slips through the straw because there's not a lot of friction, but there's lots of friction on the other side because of the angle. So one side of the string goes down, which makes the other go up, which means the frog goes up with it, all thanks to friction. So now, let's max it out. This is a super maxed out climbing frog. Just like the small version, I have a rope going through 2 tubes. I pull on one rope and the other holds on by friction. Then I switch. And it does work. It's just a lot harder to pull on the ropes, but it totally works. Whoa, just whoa. There, and then this one, and then that one, and then that one. Yeah! A giant climbing frog! All because of friction. Here's another way to defy gravity using friction. Get a plastic water bottle and fill it with rice.
Take 2.
So get a plastic water bottle and fill it with rice using a funnel. Then take a shish kebab skewer and stick it into the bottle and nothing happens. But if you tap the bottle down, the rice starts to pack in a little bit better. See how the level of rice is lower? Which means you can add more rice. Pack it down even more. And you can even use something the same diameter as the mouth of the bottle, like, say, a highlighter. And make sure all the rice is as packed in as you can get it. There. Now the rice is really packed in there. And when I stick the shish kebab skewer in, the friction between the pieces of rice and this wood is enough to lift the bottle using nothing but friction. Now, let's max it out. I filled this 20-liter water cooler jug full of rice, and it's really heavy. I wanted to see if I could lift it using nothing but friction and this dowel, which is just a round piece of wood. All right, here we go. Ah, science! I'd max it out even more, but I don't think I could lift anymore. It's okay, I can just fit. Newton's first law in 60 seconds. Newton's first law says an object in motion tends to stay in motion. So why don't they? See, if I was to throw this, it doesn't stay in motion, it doesn't keep going, it slows down and falls to the ground. Well, the whole law states an object in motion tends to stay in motion until an external force acts upon it. So what forces are acting upon this? Well, gravity for one, pulling it down towards the ground, and friction, specifically air friction, slowing this down and making it stop. Now, if you were to have something very light with a lot of surface area, it would really be affected by air friction. You wouldn't be able to throw it very far at all, no matter how hard you tried. So there you go. Newton's first law, an object in motion tends to stay in motion unless it's affected by an external force, such as friction, like air friction. So there you go. Pressure happens when you squeeze something or compress it. Solids do not compress very well. I will demonstrate. Solid? Is it compressing? No, okay. Liquids don't compress very well either. You can demonstrate this for yourself by getting a plastic water bottle and filling it right to the very top with water and putting on the cap and squeezing. You'll find that you can't really squeeze the bottle very much. But if you empty out half of the water, no, don't pour it on the floor, and then put the cap back on the bottle and try to squeeze it, you'll find that you can squeeze it a lot more. That's because gases compress much easier than solids or liquids. Here's what's going on. Say this container is, well, any container. And these magnets are air molecules. Now, I'm gonna put the magnets in pole to pole so they repel each other and wanna stay a certain distance apart, just like air molecules do. There we go, a container at normal gas pressure. Now, watch what happens when I add more gas molecules. They start to get squeezed together. And if I add more, the amount of space that each one gets is less and less. Now this container is under a lot of pressure. These molecules really want to escape through the top of the container, but they can't because I'm holding them down. If I took something like this plunger and I pushed them down even more, now they're really under pressure. They want to get out, but they can't because I'm holding them in. Now watch what happens when I let them go. They all pop out the top, and the container has returned to normal gas pressure. That's what happens when we put gas in a container like this one. These containers that hold compressed gas are made out of solid steel because you need something really strong or it might explode if you put too much gas pressure in it. That's why these are only filled up by professionals who know exactly how much pressure it can take. That is the power of pressure. Our maxed out mousetrap boat isn't the only way to give a boat propulsion. Let's look at another way using a balloon. Let's make a balloon-powered boat. All you need for that is something to be your boat and a balloon. Then you attach them together. Actually, the best way to do it is use a straw and attach the balloon to the straw using an elastic band. And then you attach it to your boat using more elastic bands, just like this. I've put a nice tape top on the boat to make it look awesome. And I also put a little bit of a riser here using just anything plastic to keep the straw nice and straight, because the question is, will our balloon-powered boat work better if it's pushing in the air or if it's pushing in the water? Well, let's do a science experiment and find out. First version, in the air. Oh, almost all the way. Now let's try it with the straw like this so it pushes into the water. Whoa, works so much better. Why? Because water is denser than air. The air coming out of the straw has to push against something to make the boat move. Water has more mass than air, so pushing against water has a better result. Now, let's max it out. This is an air compressor.
Well, actually, that is the air compressor. You see, the engine here pushes air into this tank, which works sort of like the balloon. And then it goes out this long hose, which sort of works like a straw. So let's make a maxed out air-powered boat. Ready? Just like the small boat, pushing against the air doesn't produce much thrust. Huh. Not so great. But now let's put it in the water. Pushing against the water gives me much more thrust because water is more dense than air.
Oh,
Maxed out air-powered boat! Maxed out air-powered boat! Yeah! Whoa! That's not me.
This is hydrophobic coating. Hydrophobic literally means afraid of water, but it's not actually afraid of water. The chemistry of a hydrophobic coating prevents water molecules from penetrating anything you spray it on. You can get this stuff at the hardware store, and if you want, be Science Maximites and get an adult and think of the coolest thing you could spray with hydrophobic coating. I like to use things that do not go well when you put them in water, like tissue. Yeah, doesn't look great when it gets wet. Here's a tissue coated in hydrophobic coating. Huh? Weird. Or it works the same with a paper towel. Paper towel in water, paper towel covered in hydrophobic coating, stays dry. Or how about a dinner roll? Dinner rolls really don't like water. See? Gross. But a dinner roll coated in hydrophobic coating? Weird. Just don't eat it. Now, it's time to max it out. I have coated half of my lab coat in hydrophobic coating, and the other half I have not. Hydrophobic coating, regular lab coat. Half of me is wet, and half of me is dry. What's more, half of my outfit ended up being wet and half dry because the lab coat was protecting my outfit from getting wet. Now it's time to max it out even more. We have coated my entire outfit in hydrophobic spray. My shirt, my pants, and my lab coat. The pants have been taped to rubber boots, so no water's getting in there. And my shirt has been taped to my pants, so no water's getting in there. So here's the question. Can I get into the pool and out of the pool and stay dry? Let's find out. In the pool, out of the pool, and I'm still mostly dry. Now here's what really happened. I got into the pool, and I realized I should have duct taped the pocket, because all the water went in there, down into the rubber boots, started filling up the rubber boots, and now my entire leg is full of water because the hydrophobic coating isn't letting it come out. So the hydrophobic coating isn't keeping the water out. Now it's keeping the water in. Let's take a closer look at Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
Okay. All right, let's watch it back.
When the sign hits me, I exert a force on the sign in the opposite direction. That makes the sign stop moving. It also exerts an equal force on me, causing me to fly off in this direction.
Now, if I was to push this sign, I'm not only pushing the sign this way, but my feet are pushing against the ground in the opposite direction. It's, well, it's really easier to see if I'm not standing on the ground. Oh, hold on. Okay, so, okay. So now that I'm hanging, watch. I push on the sign, but when I exert force on the sign to make it go this way, I go that way. Well, actually, it doesn't work as well because the sign isn't as heavy as I am. So wait, I have this over here. This is a barrel, and it has stuff in it, and it weighs as much as I do. Okay, so watch. If I push on the barrel like that, I go away from it as much as it goes away from me. So, there you have it. Newton's
third.
No, hold on. Newton's
third law.
Newton's third law. Okay, go.
Newton's third law. For every action, there is an equal and opposite reaction.
This is a magnet. This is a magnet. This is a magnet. This is a shoe. What's the difference? To know that, you have to know your magnets. This is a donut. It does not stick to this magnet. This is a spoon. It sticks to this magnet. These paper clips stick to this magnet. This shoe does not. So what is attracted to magnets? Only things that are ferromagnetic. Here's the difference. Horseshoe, horseshoe magnet. This one is a magnet. This one is not. But the horseshoe sticks to the horseshoe magnet because this one's a magnet and this one is ferromagnetic. Only things that are ferromagnetic are attracted to magnets. Things that are not attracted to magnets, they're not ferromagnetic. Plastic, banana, mitten, sandwich, magazine. No, but how do you know? Do you go around the world sticking a magnet to every single thing one at a time? Hey, Ma, I need you to come over. I need to see if you're ferromagnetic. No, ferromagnetic. No, you don't need to do that. First of all, only metals are ferromagnetic. So that eliminates all your clothing, your luncheon meats, your magazines, what have you. Everything that's non-metal, you don't need to worry about. Never mind, Ma, it doesn't matter. But this clock is metal. It doesn't stick. Well, not all metals are ferromagnetic. Mainly just the ones with iron, nickel, or cobalt. And there you have it. Now you know your magnets. I hit the phone on the magnet there. Okay, can you hear me, Ma? Hang up the phone. Hang up the phone, Ma. Oh, hey, how are you? You ever think to yourself, no matter what I do, I can't seem to get anywhere. I can't get enough traction? Well, you, my friend, need some more friction. Which one of these two shoes has more friction? Take a closer look. Huh? Right, bam. This one doesn't have a lot of treads. It doesn't have a lot of friction. But this one, it's got metal spikes on the bottom. This is called a cleat, and the spikes are for helping you grip onto the grass when you're playing soccer or golf, increasing its friction. Why do you think skis are smooth on the bottom? Come on, look at that. It's so smooth and glidey. My hand I can barely even touch the surface. It just slides right off. It's sort of glidey and smooth. They're smooth to help you glide across the snow, reducing their friction. Why doesn't this box slide down this ramp? Friction. This roller skate has wheels. Wheels reduce friction. But when I push the roller skate, how come it doesn't just keep rolling forever and ever and ever and ever? And going all the way around the world and writing a memoir. Say it with me. Friction. Louder. Friction. Can't hear you. Friction. A little too loud. Friction. Ease it back. Friction. How can I hang onto this rope without falling? Friction. How can I jump down on the floor without falling over? Friction. And now you know your friction. Your friction. Your friction. Come on. Uh-oh. Oh, Ramona, the friction sign is broken. Reset. Uh-oh. Our hover disc worked well. So well that we decided to build another. If we have two hover discs, then we can race them using different kinds of friction to push them along. Something that has low friction, like a dust mop, and something that has higher friction, like a pole with rubber balls at the end. Rubber has great friction. That's why we make car tires and the treads of our shoes out of rubber. Okay, we have a giant race course that we've set up. We've got two low-friction hover discs, and I'm gonna use the low-friction dust mop version to propel my hover disc. And Helena, what do you have?
I have the high-friction rubber ball stick.
Start your engines! On your marks, get set, and go!
Remember, Helena and I are using very different methods to get our hover discs moving. I'm using a low-friction dust mop, and Helena is using high-friction rubber balls. As you can see, my low-friction dust mop doesn't make enough friction with the ground for me to push myself. Helena, on the other hand, is having no problems.
Let's go! Go ahead! Defeat him! He's way back! Oh! Bit further! He's way back! In for the win! It's the winner! She crosses the line!
Yes!
And then we have our winner. Yes! Over the finish line. It feels way back over there.
Oh, man.
I'm still stuck at the second turn. Way to go, Helena.
Thank
Nice.
you.
So what was the strategy? How did it work?
Well, pretty much while I was using those red balls, I was getting friction, helping me steer.
You know what? I think we need a little bit more thrust. That would work even better if we had something pushing us even harder.
Definitely.
Wait. I have an idea. Wait, hold. I need your help. Come on.
Our pasta bridge was going to take a long time to build out of individual pieces. So we have a new plan.
Hey, Michaela.
Hey, Phil.
How you doing?
I'm great. How are you?
Good. This is Michaela. She's an undergrad in industrial engineering, right?
I am.
And you and Kyle have a new plan for how we can build our pasta bridge that's not gonna look like this.
Oh, man.
This is the best that Kyle and I could do with 20 minutes.
Okay, well, I have better.
Good, I'm glad. How are we gonna do it?
So, instead of that, we're gonna try something like this.
Oh, okay. This is sort of like a giant burrito kind of thing, right?
Yep,
But we're going to build the bridge out of this.
exactly.
We're gonna make it longer, though?
Yep, we're gonna make it 8 feet long. We have this long pole, right?
Yep.
And we have sheets of this pasta. We're gonna put them on the diagonal,
Okay.
and we're gonna roll it, but we're gonna start from this corner, and we're gonna keep rolling.
And don't
All
forget
right?
to add water.
And we gotta add water.
I'll add the
'cause-
water.
Okay.
Adding water, just like this?
Yep. It helps the pasta to stick together. So as we're rolling, we're gonna keep doing this with a bunch more sheets so that it gets really, really long, like 8 feet long. And when we're finally done rolling, we gotta spray it with some varnish,
Yep.
and so it all holds together.
Great, and then it's gonna be about this thing
Yeah,
when we're finished with it.
exactly.
This is going to be one of the parts of the deck of our bridge.
Great, so each one of these large pieces is gonna be like one single strand of pasta, and the little bridge we made.
Yeah,
We need a lot of these.
a lot.
A lot.
Yeah.
Still, it's a lot faster than doing it piece by piece with just the spaghetti.
Oh.
Every time I hold it up, you make that noise.
Oh. Oh. Oh.
Awesome. This is an egg. Eggs do not like to be dropped. Oh, fortunately, we can use the power of science to design something that'll keep the egg safe as it falls. Behold, my egg drop contraptions. The thing I really like about this experiment is there's no wrong way to do this. You can come up with any design you want and see if it works. This one here is a bunch of helium balloons. This structure is just to keep the helium balloons on so the egg can touch down very gently. Here it goes. Whoa. and the egg is unharmed, miraculously sound. That one worked really well. Success. This is a giant helium balloon that I think will work pretty much the same way because I think this balloon will drop just slowly enough that the egg can actually just touch and nothing will happen. So that didn't work. And then there's this one, which has no slowing at all. It's all designed to just absorb the impact. And the idea is that the cone will crumple and absorb the force when it hits the bottom. Oh, no! Oh, no. I think it would have worked if it hadn't turned in the air, but it did, and, well, I guess the egg is completely broken. So I'd call that one a fail. This one is the parachute. You see the egg has been nestled into this foam container, and this is a parachute that will hopefully slow the egg down. Woo! Uh-oh. Whoa. Over, good. And that one seemed to work well. Yep, the egg is totally fine. The parachute worked.
All right, egg drop experiment, totally fun experiment to do, but the question is, how do we max it out? And the answer is pumpkin drop. Same thing, except with a pumpkin instead of an egg. Come on. Okay. All right, pumpkin drop with everything attached all at once. Okay, here we go. Ready? 1, 2, 3. So what we've learned from this is the heavier something is, the more force is acting on it from gravity, which means the harder it is to slow down when it's falling. Okay, fair enough. You win this one, Gravity, but I'll beat you next time. I'm gonna get a broom. Phil's weight on 2 toilet paper rolls. Nope. Bill's weight on 4 toilet paper rolls. Nope. Bill's weight on 6 toilet paper rolls. Nope. Bill's weight on 10 toilet paper rolls. Ha! Ha ha! Phil's weight can be supported by 10 toilet paper rolls. But what if Phil jumps? Ha 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 ha! Didn't really work. Better sandcastles in 80 seconds. Building sandcastles is fun, but you can't use dry sand because it doesn't stay up very well. You have to use wet sand. But even if you use wet sand, it doesn't hold a lot of weight. But if you use sand with the power of science, it does hold the weight. Dry sand, wet sand, science sand. Here's what's going on. Say these ping pong balls are grains of sand. When they're dry, they don't hold together very well. That's why you can't build a sandcastle out of dry sand. But if you get the sand wet a little bit, the grains of sand will hold together a little better because of the surface tension of the water. That's why it's easier to build a sandcastle with wet sand, but they still won't hold much weight. But if you add something that creates even more friction between the grains of sand, like say this sandpaper, it will hold the weight. So here's what you do. Take window screen and cut it into circles. Make sure you get an adult's permission first, okay? Deal? Put in a layer of sand, pack it down, and put in a circle of window screen. And a layer of sand, pack it down, circle of window screen. Then, you guessed it, layer of sand, pack it down, circle of window screen. The window screens are gonna add more friction between the grains of sand and will make your sandcastle strong. Strong with the power of science. And then you can put lots of weight on it. And there you go. Sand with the power of science. Ha ha! Okay, I had to max it out. Let's see how strong science sand really is. Huh? Ha 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 ha! Science! Today, we're taking a closer look at chemistry. Ooh. Chemistry is the science of atoms and molecules, the things that make up all matter, and how they interact with each other. Take, for example, this glow stick. Actually, don't take it, because I kind of need it. The glow stick doesn't glow until you... The glow stick doesn't glow until you break the barrier and mix the two chemicals, and they start to glow. Huh? Pretty cool, huh? Chemistry. Now, the chemical reaction we're looking at today is the old vinegar and baking soda volcano. But this reaction doesn't have anything to do with volcanoes. It's chemistry. Now, this experiment is totally safe, but I do recommend you get an adult's permission before you do it because it's very messy. Yeah. First, you're gonna want baking soda and vinegar. These are your two main ingredients, but you'll also want dish soap and red food coloring if you want it to look a little bit more like lava. Now, I like to mix the baking soda, red food coloring, and dish soap together with a little warm water, so all you have to do is add the vinegar. And when you do, this is what happens. And there you go, chemical reaction. Now, I know what you're thinking. You're thinking, Phil, how much vinegar or baking soda do I use? Well, I'm not gonna tell you. This is where you can be science maximites. Try different amounts. More vinegar, more baking soda, more dish soap. Who knows? Write down the amounts each time you use it and find out what amounts work best. That's called science. That's good, Ramona. Put it in the background. Put the sign in the background. Yeah, in the BG. I love the BG. Chemicals, 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 chemicals. What are chemicals? Are they things you have in a lab in a jar that say chemical on them? Well, yes. But if that's all you think chemicals are, then you need to know your chemicals. Turns out the stuff in the jar is a chemical, but the jar itself also made of chemicals. The table I'm putting it on, made of chemicals. My lunch, chemicals. Roller skate, chemicals. My jacket, chemicals. This guitar, chemicals. My shoe, chemicals. This watch, chemicals. This fish, chemicals. 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 Me, chemicals. You, chemicals. Ramona, chemicals. No, I said your chemicals. Never mind. This is it. The periodic table of the elements. All matter in the universe is made up of these pure elements. They go together in different ways to make up everything. All matter. Think of it like building blocks. These little atoms are some of the elements on this periodic table. You got 1 oxygen, 2 hydrogen, bam, you got a water molecule. 1 carbon, 2 oxygen, hey, it's carbon dioxide. 2 carbon, 2 oxygen, 4 hydrogen, skadoosh, vinegar. 1 sodium, 1 chlorine, hey, that's salt. All matter in the universe is just the stuff on here combining into these. And now, you know your chemicals. Sugar. All right, Talina, you ready?
Yep.
You're gonna pour all your baking soda in the fish tank, and I'm gonna pour the vinegar into this bucket, because you don't wanna pour them together right away. Okay, you ready?
Yep.
Okay, go for it. When you're doing your PhD in chemistry, do you get to do stuff like this?
Yeah.
Really?
Got to do a lot of fun reactions in the lab.
Oh, I'm jealous. Have you ever done this much vinegar and baking soda in one time?
I can't say I ever have.
There you go. That's what I like to hear. I already put the soap in the bucket so it would mix with the vinegar when I poured it in. Are you done your baking soda already?
I am.
I'll pour faster. Oh, faster.
It smells vinegary.
It smells vinegar. It makes me want French fries. Okay, Talina, you take this very full bucket of vinegar and dish soap.
Thank you.
I will take this one. Uh-oh, we still have our third bucket. Okay, I'll do these both at the same time. Okay, ready? On the count of 3. 1, 2, 3. Whoa! 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 Wow.
Okay.
That's awesome. So the one thing it didn't do, it didn't shoot up in the air though.
Yeah, it's because the top is quite open, so you would need to constrict it to get it to shoot up.
Oh, yeah, because we're using just sort of a square, a rectangular prism container. We should get something that's maybe something more like our vinegar bottle, right? Because there's lots of space down here, but then it forces it into a tighter opening at the top there, like a volcano.
Yep.
And what else can we do to make it even more powerful, max it out?
Vinegar is only 5% acid, the rest is water, so you could try using 100%.
So what kind of acid is vinegar?
It's acetic acid.
So vinegar is actually only 5% acetic acid?
Yep.
and 95% water. So you can get 100% acetic acid?
Yeah.
Can you get 100% acetic acid?
Yes.
Awesome. Why don't we get a container that's sort of shaped like a funnel, like a volcano,
Yeah.
and 100% acetic acid, and we'll do it again.
Sounds good.
All right, let's do it. This is a balloon, and this is an orange. When you put them together, a chemical reaction happens. How'd you go in there for a minute, didn't I? No? No? All right. Well, you can actually do a chemical reaction between a balloon and an orange. You see, balloons are made of latex, which is a kind of polymer that's very, very stretchy. And orange peels contain a chemical called limonene. Limonene breaks down latex. So, we have 3 questions. The first is, why does this happen? Well, like I said, it's all chemistry. You see, balloons are made of polymers, chains of molecules held together by chemical bonds. A limonene molecule attacks those bonds. Nom nom nom, nom nom nom, nom nom nom, delicious. And breaks it, that separates the polymers, and that pops the balloon. But remember, it only works with natural latex. So make sure you're using natural latex balloons. Second question, why do they call it limonene when it's in orange peels? I mean, yes, it's in lime peels and lemon peels, but the chemical itself smells like oranges. They should call it orangenine or citrus fruitinide or... Anyway, third question, should we max it out? Of course we should, come on. 200 balloons versus 2 bottles of limonene. Ready? Go! Our maxed out rocket worked great. Now to make it look more like a rocket.
So we have a mesh bag here to put the antacid in.
Right.
And we have some paper clips attached to it.
And what are the paper clips for?
Well, Phil, we have a magnet.
Ah.
And so the magnet sticks to the paper clip.
And so that's what we have here. You see, the bag is full of the antacid tablets, which we put through the mouth of the bottle, and the magnet is holding the paper clips on the other side of the plastic, so we can sort of move it along. So we can start with the bag over here where the water's down there, but now we attach the launcher like so. All this effort is to keep the reaction from happening until the bottle's on the launcher and we're ready to go. And then, as we pull the bottle over, we bring the bag up this side, and there, the water and the antacid have never touched.
No reaction.
All you need to do now is we pull this magnet away, and the bag will fall into the water, and then we will have the launcher down here, and we pull the release, and the rocket will go. We add some weight to the launcher to help keep it in place. Okay, right, wait, glasses.
Safety first.
Okay, ready? And then we pull the string with the magnet. That drops the bag of antacid tablets in the water and starts the chemical reaction. Because we have a latch holding the bottle down, we can wait until the chemical reaction happens fully. And there's a lot of gas pressure in the rocket before...
3,
2, 1.
Launch! Woo! That worked.
Yeah, I hit the ceiling. I think we need to do this outside.
Yeah, I think we definitely have to do it outside.
All right, totally great. Weird. Anyway, I was saying we should put 3 or 4 of... 3, 2, 1, go! There it is. Yeah! We tried it outside and it worked great. The only thing left was to max it out even more. So, larger chamber?
Yep, more antacid.
More antacid, more air, more water.
Absolutely.
Bigger rocket. Okay, so you know what? I know how to splice 2 bottles together, and we can increase the size of the chamber. is sodium acetate. How do you get sodium acetate? Well, when you do a vinegar and baking soda reaction, what you have left once the reaction is finished is sodium acetate. It's a crystal, and you can do something fun with it that may seem familiar. You make a supersaturated solution of sodium acetate by heating water and dissolving as much as you can, and then when it cools, you can get the crystals to reform. Now, if you did this with sugar, you could make a sugar pop, which we've done before. If you do it with salt, you could make a salt pop, which is less appealing. And if you do it with sodium acetate, you can do this. Just like with the sugar pop, all it needs is a seed crystal to get the crystals to reform. But unlike sugar, which takes a few days, sodium acetate recrystallizes right before your eyes. Because we heated the water, it allowed more crystals to dissolve in it. Ooh. But then it cooled down afterward. There's more crystals sitting around in this water than there should be at this temperature. They want to turn back into crystals, and all they need is something to start them going. I've colored this one green because, I don't know, science. Maybe it'll look cool. A tiny crystal on the end of the stick is all we need to start the reaction happening. Whoa! Wow. And there you go, sodium acetate. That one wasn't done yet. This is a basketball. It bounces. This is a golf ball. It bounces. But it never bounces as high as where I dropped it from. But watch as I put the golf ball on top of the basketball. Whoa! Why does the golf ball bounce higher than where I dropped it from? How is this possible? I only bounced the golf ball from 1 meter high. So what's going on? Well, as the basketball hits the ground, it compresses, storing the potential energy of its bounce, about to give that energy back as it bounces up again. But this energy works as a springboard for the golf ball. And since the golf ball has a lot less mass than the basketball, the upwards kinetic energy of the basketball is given to the golf ball. So, let's max it out. Ball, on a ball, on a ball. 3-ball bounce. Oh, did you see that? Ball, on a ball, on a ball, on a ball. Quadruple ball bounce. Oh, oh. Oh. No, wait. Turns out getting 4 balls to drop straight down on top of each other is pretty difficult. So, we know the mass of the ball is important. Why don't we max it out in a different way? This is a Swiss ball for exercising. It has a lot more mass than a golf ball. So, let's try it out. There you go. The transfer of energy between balls. A great way to lose golf balls. Hey, Science Maximites, slippery. But that's okay, because today we're talking about friction. Friction is a force that is everywhere and happens when any one thing rubs against any other thing. We do lots of things to increase friction, like wear shoes with big treads on them. And we can do things to reduce friction, like the experiment we're doing today. We're gonna build a hover disc, and it's very easy. You take some cardboard and cut it into a circle, just like this. Then put a hole in the middle of the circle. You might want an adult to help you with that. And then take a plastic drink bottle cap, like this. I like use the ones that you get on sport bottles because they have a little nozzle that pops open or closed. And then you glue it around the circle and you get this. Then you need a balloon. So you blow up your balloon. I know you know that step. And then twist the balloon so it doesn't get away from you. When it's nice and twisted, you can stick it over the drink bottle cap like this, and then untwist it. And this is why I like to use the plastic drink bottle caps that come from sport bottles, because you can open it
when you want. And when you do, your disc rides on a cushion of air, reducing the friction with the table, and it's almost like it's sliding on ice. You can also use CDs if you want to do a different design. Just make sure you're using CDs you never want to listen to again. Now, if any of this is too fast, don't worry. You can always go to the Science Max website, where we have all of the instructions. Greetings, Science Maximites. Today we're using fizzy drinks in our experiments. And a fizzy drink is just water with bubbles of carbon dioxide gas dissolved in it. So I thought, since we exhale carbon dioxide, I could make a fizzy drink by just blowing bubbles in this water. Doesn't seem to be working though, does it? I don't see any bubbles, do you? No. Water does absorb carbon dioxide gas, but I don't have a fizzy drink. Weird. Time to check the book of science. Oh, in order to make bubbles, you have to have pressure. So... this is an air compressor. It takes air and compresses it, puts it under pressure. So... the container needs to be pressurized. Okay. When you get a container of a fizzy drink, the carbon dioxide gas is put in there under pressure, and it stays in there under pressure until you release it. That's the sound of the pressure being released. And when it is released, the carbon dioxide gas starts to expand. And when it expands, it creates bubbles. And that's what makes your fizzy drink. This process takes a while to run out, but eventually it will become flat. No more bubbles. But what if there was a way to release all of that carbonation all in one go? Well, there is. And for this experiment, all you need is your favorite brand of fizzy drink, Science Max brand Diet Science Cola, 100% science, 0 calories. And your favorite candy, like these Science Experiments. All the minty flavor that comes from pure science. So, all you need to do is open this up, take one of these, and put it in here with an adult's permission, because it can get kind of messy. What's going on here is all of the carbonation that was in the bottle is now being released much more rapidly than it would have been before. Now, why does this happen? Well, if you look at a carbonated beverage, you'll see that the bubbles don't come from everywhere. They come from the inside of the glass, or in this case, a lot are coming from the straw. And that's because the carbon dioxide bubbles like to find a little imperfection, something to hold on to in order to expand and bubble out. And a candy, such as this, has a ton of little tiny microscopic imperfections. So when you drop it in, there's a lot more places for the bubbles to attach, and that makes the carbonation happen a lot quicker. But remember, this is not a chemical reaction. It all has to do with carbonation. So that's what we're gonna be looking at today. Air pressure, more pressure, less pressure, and of course, we're gonna be maxing out this experiment. Nothing like a fizzy glass of water. And now there are ways for you to carbonate water at home with something like this Science Max Carbonation Station. You have a bottle of compressed carbon dioxide gas that's hooked up. You take a bottle of tap water, attach it, and carbonate it. Voila! Carbonated water. But this is Science Max. Why just carbonate water? Let's carbonate everything! Let's carbonate pickle juice. It's actually amazing. Milk. It's like milk meets water, kind of very odd. Chocolate milk? Oh no, that's way better. Carbonated mustard. Carbonated tomato juice, carbonated hot sauce. No, wait, carbonated... That was the hot sauce. No. Carbonated clam chowder. Oh, there you go. Carbonation, not just for water anymore. It is definitely not for clam chowder. No, that's just a big bowl of no. Never again. So here we go.
Amazing.
The friction ramp, it's pretty simple. You just take, I've got blocks of wood with different surfaces.
Amazing.
And then you just slide them down the ramp.
Right. So cool.
Yeah, so what if, to max it out, what if this is us?
We're a block of wood?
No, I mean like we are on the block of wood and then we can try changing the bottom. I guess a block of wood isn't the right thing to use though.
Right, yeah. Maybe we could use like a sled.
Oh, yeah, okay, like a snow sled. That's a great idea. Okay, so we'll tell you what. I will portal in a sled for us.
Are you sure you want to portal it in?
I'm sure. Just stand back
Okay.
though. Okay. Ha!
Ah, there we go.
Maxed out friction slide! You ready, Sarah?
Yeah, I'm ready.
Okay, here we go.
All right.
Sarah and I pushed each other around on the sled, which was fun, but it was also tiring. It's pretty hard. This is my turn. My turn.
All right.
Oh, yeah! Whoa, friction! Yeah, friction! Yeah! Yeah, friction! But we soon realized it'd be pretty hard to measure how much friction there was. You know how hard you were pushing?
I had no idea how hard I was pushing.
A lot, but that doesn't really help in science terms. So
Exactly.
what do we do?
Well, with your first experiment, you used a ramp. Could we maybe put a ramp up in here?
In here?
In here, yeah.
I guess.
Then we can measure also how far we go so we know how much friction is being used.
Right, so we have our control, and then we have all the, just like the blocks.
Exactly, just like the block.
Okay, great. So we'll get the ramp, we'll get a bunch of wood,
Yes.
we'll get some tools.
Yeah.
Whoa. This is a Prince Rupert's drop. It's a piece of glass that has a long snaky tail and a bulb at one end. So what's so interesting about a glass tadpole? Well, I'll show you. And remember, this is just glass. Oh, Prince Rupert's drops are very strong, almost as strong as steel. It's all in how they're made. Molten glass is dropped into cold water. What happens is the outer part of the drop cools off first, leaving the inner part still hot. When the inner part eventually cools, it contracts, pulling everything in tighter and tighter, keeping it under a lot of tension. And because it's round, the force you put on it is distributed all the way around, just like the force is distributed on an arched bridge. Until you get to the tail. Just the tiniest break in the tail, and it explodes. All that energy is released in a chain reaction. Why it's so strong you can hammer on one end, but explodes when you break the other, puzzled scientists for centuries. But now we know it's all in how it's made.
The Wizard Academy. All you have to do is demonstrate true magic, and you will be granted entry.
Send in the next applicant. Okay, don't let them see you. Don't let them see you. Okay, magic smoke. And here we go. Big entrance. Behold, it is I, Overwhelmo. You again. I only have to demonstrate magic one time, and you have to let me into the Wizard Academy. And last time does not count. So prepare for your mind to be boggled and your eyes to also be boggled, because I shall do a trick. I will just get to it. Here is a book, behold! And now, feast your stupefaction as I produce another book, ha-ha! And then 2 or 3 more times, behold, that's good. Behold! And now, look upon the wonderment as I stack these books on top of each other, like this. And now, feast more stupefaction as I cleverly move the books off the table. And now comes the magic word. Now, I say the magic word. The magic word! And behold, the book is levitating. It is completely off the table. I have done it. Magic!
No.
No?
Not magic, that's science.
But the book is levitating.
No.
Look, it's not even touching the table.
No, it's being supported by the books below because of the center of mass.
Preposterous.
I'm afraid it's very preposterous. Each book is balanced on the one below in a way that the center of mass is behind the edge of the book below. And the entire stack's center of mass is behind the edge of the table. So it may look like magic, but it's science.
So, I can't get into the Wizard Academy?
No, I'm afraid not.
Aye, good. Alakazam! You will rule the day that Overwhelmo did not. I will return, and then you will see. Oh, ow.
This is a bike tire. It's pretty light, but I still can't hold it from the end of the pole like this with one hand. Nope, nope. But I can if I get it spinning fast enough. I just use this drill, and then I get... Okay, so this is gonna be awfully hard to do with one person. Oh, this is the perfect opportunity to use the Trevor button. Haha, Trevor button. Hey, Trevor from the Science Max build team. What are you doing?
Maxing this out.
Oh, right on. Can you give me a hand for a second?
Sure.
Awesome. Okay, so you take this drill, and we're gonna get this wheel spinning really fast.
Okay. I don't know if it's,
No, I don't wanna know.
I don't know if I remember to...
No, it's fine. Max it out. We gotta max it out. So, because it's spinning, I can hold this heavy weight in the air. How is this possible? Because the wheel is basically a top. The forces that prevent a top tipping, angular momentum, are still working here. This angular momentum resists a change in direction this way, which is how gravity would want it to tip. Interestingly, these same forces also keep it spinning around me in a circle. So, I can lift a heavy weight in the air just by spinning it. Awesome max head experiment, Trevor.
Yeah!
What was that?
It's my science confetti high five I just made.
Well, you know what we should do?
What?
We should max it out. Yeah, we can make a giant one and then a whole bunch of confetti in it, and then people like jump up and do more confetti that would come out, right? And then so what would happen is there would be all this Trevor? Mouse trap. Like I said, we are going to be using mousetraps. Mousetraps as a form of propulsion. That's the force that makes things go, and we are going to be making a boat go. And what is the thing that's going to make this boat go? A mouse. Oh, it's not set. Sorry, I'm really jumpy. Anyway, we're gonna be using a mousetrap. And don't worry, no mice are gonna be harmed in the making of this or any Science Max episode, but mousetraps are really great because they can store energy in the spring. If you see, there's a spring that makes this bar want to snap back, but we can put energy into the spring and store it and then use that energy as it unwinds the spring to propel our boat. But it's a little more complicated than just this, so come on, I'll show you. What we're gonna do is build this. This is the mousetrap boat, and it works like this. I've got the mousetrap, and it's attached to a long arm. That arm has a string on it, and it goes around the paddle wheel, and as the mousetrap unwinds, the paddle wheel spins like that, which pushes the boat forward. Now, it looks kind of complicated, but it's actually quite simple to make, and here's what you need. My mousetrap boat is made with styrofoam, craft sticks, and elastics. You'll also want a pencil, plastic drink caps, a shish kebab skewer, small zip ties, string, and of course your mousetrap. Now, mousetraps can hurt your fingers, so get an adult to help you when you use them. Start with 2 pieces of styrofoam. I like to cut mine into this shape, but the only really important thing is that they're the same size. Your paddle wheel is made from a circle of styrofoam with it penciled through the middle, and it will go across like this. To make the paddle wheel, I use cut pieces of craft stick, or they can be plastic, and make some cuts and then put them in like this, and that is what will make your paddles on the paddle wheel, because that's the wheel and that's the paddle wheel. That's why they call it that. Stick drink caps to the ends of the pencil after sticking it through the styrofoam. I like to use a few craft sticks and elastics to help give the styrofoam strength. Next is the mousetrap, which you want to glue down to a frame of 4 craft sticks. Attach the frame to the boat with elastics, then attach the shish kebab skewer or a pencil to the mousetrap with zip ties. I like to put some craft sticks on the end to make it easier to tie the string to it. Wrap the other end around the paddle wheel pencil, and remember you need enough string so that your stick can lie flat.
Okay, let's try it out.
Wind up the paddle wheel. This will be a little hard as the spring will pull back, but that's where you're storing the energy. And when it's wound up, put it in the water and
Let it go. The paddle wheel turns because the mousetrap is transferring energy that we put in earlier, and it goes all the way.
we stored the energy in the tension of the spring. Now that tension is pulling the mousetrap, the stick, and the string, which turns the paddle wheel and makes the boat go.
Mousetrap-powered boat!
If you want more detailed instructions or other designs, look up Mousetrap Boat.
And there you have it, the mousetrap-powered paddle wheel boat. And this is what we're going to max out today. Come on. This is a chain of beads, and this is glass. Now, if I was to drop the chain of beads, what'll happen? It will fall. Yes, that's right, it'll fall because of gravity. But watch this. This side goes up. Why? Because of gravity. Wait a minute. Why does one side go up because of gravity? Well, it gets a little complicated, but I can explain. But I think I'll have to put the beads back in the glass. Okay, so what's going on? Well, when this part of the chain starts falling out, it gets longer and longer, and it has more mass than this side of the chain. And if it has more mass, then it has more inertia. And when it starts yanking out very hard, this side of the chain gets yanked up out of the glass very quickly. When it gets yanked up hard, it flies into the air. But then, of course, the direction has to change, so it goes around a curve and then goes back down. Because of the speed that it's going, that curve starts lifting up over the top of the glass. And that's how it works. There's a big difference in energy because this chain falls far. I try it from here, and it doesn't work as well. Why? Because the drop from here to here isn't as big. You want lots of force acting on the falling chain, which means the higher you do it from, the better it works. So maybe we should max it out. Yeah. But wait, we should wait for it to stop. And now let's max it out. This is a really long chain, and this is a really long drop. Let's see what happens. Whoa! Look at that! Whoa! Super maxed out! Science! Now we're gonna talk about tension. What's tension? One more than 9-shin. Get it? Because tension and 9-shin, that's, okay, tension is the force that we usually talk about when we think about pulling a rope or a chain or something like that, because you know the old expression, you can't push a rope. But today we are gonna push a rope. I have a rope right here, and I'm going to push it using another force called flexion. I've got some pieces of plastic here, and they bend or flex. And when they do, they want to spring back. But I'm going to prevent them from springing back by putting them in between these knots. And look, the rope now stays up. And I take another piece, and I stick it on this knot, and then I bend it all the way. This is not terrifying. Really, it's not terrifying at all. Okay, good. And then I take this piece, and I put it here, and I bend it around, and so now we have a rope that's being pushed, and we're defying gravity, and we're making a cool art sculpture. All right, one more here. Ooh, okay, here we go. And flexing. And whoa. Ha-ha! There you go. I've pushed a rope, defied gravity, and made a cool art sculpture. Okay, well, I guess technically I haven't really pushed the rope because we're still pulling from each knot. And I guess I haven't really defied gravity because that one's sitting on the table and all the others are sitting on top of that. But you can't argue that I made a cool art sculpture. Ha-ha! Science. Here is an experiment you can do at home with friction. This is a toy boat. Yes, you guessed that right. And this is a wooden plank. Correct, that's 2 for 2. I put the boat on the ramp and watch what happens. Nothing! The reason why is because the friction between the boat and the ramp is enough to counteract the force of gravity trying to pull it down. But watch what happens if I raise the ramp to the right height, the boat slides down because the friction isn't enough and gravity pulls it down. But when we change surfaces to this carpet, let's see what happens. Same angle, I can raise it higher, 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 because there's more friction between the carpet and the boat than there was between the wood and the boat. Greetings, Science Maximites. My name is Phil, and this is Science Max Experiments at Large. Today, we're going to be looking at earthquakes. Earthquakes! Huh. Today, we're going to be looking at how to build something. That was supposed to happen earlier. Today, we're going to be looking at how to build something that stands up to the shaking of an earthquake. Earthquakes happen when two plates on the Earth's surface rub together, and it causes the ground to shake. It causes the ground to shake. Sometimes it shakes a little, sometimes it shakes a lot. Chances are you do not live in a place that has earthquakes. But if you do, ask an adult what to do during an earthquake so you can be safe. Modern buildings that are built in earthquake zones are designed to withstand the shaking. But how do scientists and engineers build a building that stands up to the shaking of an earthquake? Well, that's what we're going to be looking at today. First thing we have to do is simulate an earthquake. We're going to build a shaker table. And here's what you need. 2 books and... 2 books, 4 elastic bands, and 4 rubber balls. Oh, wait. Okay. 4 rubber balls. All right, so the first thing you do is actually take your 4 elastic bands and wrap them around your books. Put 1 set on one side, 1 set on the other side, till you have that. Then you take your 4 balls and you stick them in between the books in the middle-ish area. But you don't want to have them too close to the edges. And now 2 at the back. And ta-da! You've made your own shaker table. What are you shaking, you ask? I will show you. You build a tower. Like this one here that I built out of building blocks. So here's what you do. You'll need your base to be securely attached to the shaker table. I use painter's tape because it'll come off again without harming the books. And what I want to find out is just how much shaking this tower can take before it falls apart. Ready? Oh. And there it goes. And when you've done that, what you do is you be a Science Maximite and you design another tower. And you tape it down to your shaker table and see if you can make this tower fall down in an earthquake. And if you built it really well, it probably won't. But you don't have to just use building blocks. There's all kinds of other materials you can use. Check out this building, which is really tall, and you'll see there's a cup at the top, and that's for a baseball. Put it up at the top, and that means there's a weight up there. And then we shake it, and we see what happens. Oh no! Oh, there it goes. This is water. Things float on water, like pool noodles and wood and toy boats. And now we're gonna do an experiment with how paint floats on water. How's this supposed to work again? Oh! I'm supposed to take the paint out of the can first. This is a fun experiment you can do at home. All you need is a container, some water, and paint. But not just any paint, special paint you use for hydro dipping. That's hydro, meaning water, and dipping, meaning dipping. Carefully pour the paint on the water and add a few different colors. Then take a stick to swirl it up into a pattern. Then you get something you want to paint, and you carefully put it in like so. But don't pull it out as soon as you get it in. You have to spread the paint away because it'll stick when you bring it back out. And then when you pull it out, whoa!
hydro dip. Let that dry, and then you have a very cool painted toy. Let's do some other stuff. This is a bike helmet. If you put tape on what you're painting, you can remove it later to make parts that aren't painted. Skateboard. Whoa! Oh, that's pretty cool. Now to max it out, hydro dip pants. Wearing the pants when you do this is super messy and not something you should try at home. But the results weren't bad. Science pants! Science pants! Science pants. One of the ways you can experience the power of water is watching it wash away dirt. You can experiment with this yourself by making your own erosion table. To make your own, fill a plastic tub with sand and tilt it up. Cut a hole in the tub at the low end and put a hose with a trickle of water at the high end. Then to complete your model, fill it with a little happy town. This small model shows how rivers cut their course to the ocean by following the lowest point. Try to design your town and the layout of the ground so the river goes around the buildings. I'll see you later. I'm gonna take a swim in the river now. There are lots of ways to experiment. Change the amount of water, or the steepness of the angle. Look at the soil, it's all getting eroded over here. Or the way the town is laid out. Every time you do it, the river goes in a different direction. And have fun.
Oh, phew, I'm tired. I'm just gonna lie down.
And that is the power of water. Okay, Science Maximites, prepare to hurtle through the cosmos. I am Captain Phil, and today we're going to be building rockets on Science Max. Now, we've built rockets before, like this one, powered by air pressure. And this one, stomp rockets, which were also technically powered by air pressure. Air pressure rocket! But today, Science Maximites, we are going to be building rockets powered by chemistry! Chemical-powered rockets! Away! Okay, I promise it'll be more exciting than that. Because today, Science Maximites, we are going to be looking at chemistry. Chemistry is when two molecules combine to make another molecule. Like magic, ooh. So let's take a look at what will be powering our chemical rocket. This, it's an antacid tablet. When you put an antacid tablet in water, it makes little bubbles of carbon dioxide gas. This happens because of a reaction between two kinds of molecules called acids and bases. Like vinegar and baking soda, but all contained in a small package that won't start working until you put it in water. If we contain the reaction, the carbon dioxide gas builds up and creates pressure. High five for science. All right, so let's look at our chemical-powered rocket. What you need is one of these. This is a film canister. And ask your parents what that actually means, because they're not used for holding film anymore. You can get these at craft stores, though, to hold paint or little things. But really, all you need is a plastic container with a good lid that snaps on nice and tight and keeps the air in. And then, of course, what you need are your antacid tablets and a little bit of water. So pour in some water and then put in your antacid tablet and snap the lid on. Flip it over and wait for the carbon dioxide gas to build up, which will build up pressure, which will launch your rocket. Ha-ha! So there you go, a chemical-powered rocket. I'm an acid, and I'm a base, and we are enemies. Whoa! Well, we're not really enemies. Yeah, that's true. It's all about how we react chemically. You see, as an acid, I really want to give protons away. Protons? Who needs your protons? Get your protons here. Protons, I got more than I want. I don't need them anymore. And bases, we need protons. We'll do anything to get them. Protons, you can protons away. I'll take some protons. You think that when you get these two together, you'd have some pretty great chemistry. But the truth is, when they're together, they often don't react. Whoa. That is, until water gets involved. Once you have water, acids and bases react. Whoa. Here, take some protons. All your bases belong to us. Here you go, take some protons. I don't need more. I want more. I want more protons. Here. Water is a solvent, allowing the chemical reactions to take place. Depending on the strength of the acids and bases, that reaction can be mild, Would you like a proton?
Oh, no, really, I could.
Please take it.
Oh, well, thank you, that's very generous.
Have another.
No, perhaps, maybe I will.
Here's
Yes,
one.
Okay, maybe just one.
But if the acids and bases are strong, the chemical reaction can be really extreme. This is what's going on in the antacid tablet, and why, without water, nothing happens.
Oh, water!
Water! Come on! What'd you do?
What?
And that's the last one.
Lisa and I are maxing out our chemical-powered rocket, not by making it bigger, but by making more of them. How many more? 400 caps all glued down, 400 antacid tablets, or part of, all glued down, and they're glued on this fancy-pantsy spinning surface. So we rotate this part upside down. We fill each container with a little water and snap it on underneath. This way, the antacid tablet and the water don't mix until we flip it back over. It also allows us time to snap them all on. Okay, ready?
Ready.
All right, 400 containers. Here we go.
Let's do it.
Once we flipped the board back over, the reaction started taking place, building up carbon dioxide gas and increasing the pressure until...
What do you think?
Oh, yeah. Oh, yeah.
Oh my goodness!
It's good luck if you catch one.
Wow, that one went really high. Oh!
Awesome! That totally was great. Wow. Okay, so high fives on that.
Yep.
That worked spectacularly.
That was awesome.
So we've done this.
Let's go bigger.
Let's go bigger.
Bigger.
Okay. So let's go and we'll clean this up afterwards.
Yeah,
okay.
let's do it.
Okay, let it go. Whoa. Whoa.
Help, I'm being crushed by all this pressure. A whole kilogram is being pushed down on every square centimeter of my body. 103 kilopascals.
Actually, 1 kilogram for every square centimeter on your body is the exact kind of pressure that you and I are under at all times every day. We don't notice it because we're used to it, but it sounds like a lot, doesn't it? Well, it is. Here's an experiment you can do with a plastic bottle. Say at room temperature, there are 10 million air molecules in here. Doesn't really matter how many, but we'll say there's 10 million at normal room temperature. What happens if I heat up the air inside this bottle? This is warm water. What I'm trying to do is heat up the air inside the bottle because the air molecules, when they get hotter, move faster and need more room. So the 10 million air molecules are starting to escape out the mouth of the bottle and reducing the number of air molecules inside. And now I take the bottle out and cap it. Because the air molecules heated up and speeded up, they needed more room. Now there's less of them in the bottle. There's about 4 million air molecules inside this bottle, but they're all hot air molecules and they have a higher pressure, and you don't notice it because the air out here isn't crushing the bottle. But watch what happens if I cool the air inside the bottle. This is ice water. So what's happening now is the molecules are slowing down and they need less space. So they need less room and they're being crushed by the pressure on the outside of the bottle. Ha-ha! It has been crushed because the colder air molecules don't need the same kind of room as the hot air molecules. The room temperature air has crushed the bottle. The air inside has a lower pressure than the air outside. Pretty amazing. Even more amazing when we max it out. This is a steel drum. What we've done is we put some water in it and we're heating it up to boiling so there's nothing but hot air inside the drum. This is an airtight cap, which we use to seal the drum. And now we cool the drum off. Hey, Trevor, give me a hand. Ready? 1, 2, 3, you lift! That's good. This pool is filled with ice. What we're doing now is cooling off the steel drum, which will cool off the air inside it. Which means, eventually, the air inside the steel drum will be much lower pressure than the air outside the steel drum. Because this steel drum has a lot more volume than a 2-liter pop bottle, it takes a lot longer for the air to cool down. The other thing to think about is that it's a steel drum. I could stand on it and it wouldn't even dent. But sure enough, after a few minutes... Whoa! Check it out! The barrel has totally crushed. The low pressure air inside the barrel wasn't enough to withstand the force of the regular air pressure that you and I walk through every day. The air pressure all around us is enough to crush a steel drum. How cool is that? All right, pliers, battery, copper wire. Now, if you've already done the electromagnet experiment, here's another experiment that uses all the same materials plus these. Ha! Neodymium magnets, some of the strongest magnets you can get. So, here's what you need. A battery, some neodymium magnets the same diameter as your battery, copper wire, and some pliers. So here's what you do. First thing is you put the batteries and the magnets together like that. Then what you want to do is bend the wire so it's touching the top of the battery and goes around the battery and then touches the magnets at the bottom. Here's what that might look like. I say might because you can do any shape you want. I've made a coil here, and if you put it over the battery, you'll see it only touches the very top of the battery and the magnets at the bottom. And if I let it go, it spins. It's a homopolar motor. What happens is the battery sends an electric current through the copper wire, and that turns it into an electromagnet, which is attracted to the magnets at the bottom, and it spins. So, now, let's max it out. Aha! A D-cell battery, which is larger and, of course, larger neodymium magnets. And you do the same thing. Make a coil that only touches the battery at the top and at the magnet, and ha-ha! It spins! Maxed out homopolar motor. But don't worry, this is not the biggest size we're gonna do. Come on. Maxed out homopolar motor. I have 27 D-cell batteries, a giant copper tube, and a neodymium magnet. So I'm just gonna, and then we get rid of that. Put this down. Okay, so the first thing I do is attach the neodymium magnet to the batteries. And I've got all the batteries taped together here so they'll sort of stand up like this. Huh? Giant stack of D-cell batteries. Okay, now what I do is I take the copper coil. I take the copper coil. I need to get. Okay, hold on. I got this. I just need to get the copper coil there. I did it. Okay, so I take the copper and I put it on top of the D-cell batteries like this, and then I let it go. Let it go. Nope, whoa. Homopolar motor. Okay, so that didn't work. But that's okay. I like it when it doesn't work, because that's science. It's not science if it works perfectly every time. I mean, you gotta have some room for improvement.
A delicious plate of cheese and crackers, my favorite snack. But these crackers are pretty salty, so I should probably pour myself a glass of water first, huh? No! My cheese and crackers! Why? Why does this happen? Why does the water stick to the glass? Well, because of science. And the reason why it happens gets a little complicated, but it boils down to this one simple thing. Water likes to stick to things. Huh? Did you see? Did you see how it stuck? No, of course you didn't. You know why? Because it only sticks on a small scale. See those drops of water? That's water sticking to the surface. But it only works when the surface tension of the water is less than the force of gravity, which is why water drops fall when they get bigger. So it sticks to things. That still doesn't explain why you can pour water out of some containers without any drips, and other containers make it nearly impossible. It's all about the angle. Water will flow very easily when there isn't a large change in direction, like around the curved top of this glass. But when there's a big change in direction, like at the mouth of this teapot, the water can't make that turn as easily. This is also why pouring from a full glass is much messier than one that's less full. Pouring out of a full glass, the water only needs to change direction this much to flow down the side. But from a half-full glass, the water would need to change direction this much. So all this happens because water likes to stick to things. So let's do an experiment and coat this glass with hydrophobic spray. Now, hydrophobic coatings repel water. So if it's repelling the water from the outside of the glass, will we still have the same problem? Well, let's find out. Hydrophobic coated glass, non-hydrophobic coated glass, or just regular glass. Water likes to stick to surfaces, but it can't stick to one coated in hydrophobic coating. That's impressive. Should we try something else? Well, that's one way to solve the dribbling glass problem. Except you can't coat your glasses at home with hydrophobic coating because it's not good to eat. The secret is using a container that has a very sharp angle between where you're pouring the water and the underside of the glass, like this jug. And there you go. Now I can enjoy a nice glass of water with my cheese and crackers. Oh, right. Wait, hold on. I will remake the crackers into, see, look, see, it's fine. It's fine. I'm not really gonna eat that. I'm just kidding. Chris and I are maxing out our hydraulic crusher.
Yes. Before we get to that, I have a little game I want to play.
Okay, great.
Okay. You can pick either the small one.
The big one.
Okay.
So what's the game?
Simple thumb war. I'm gonna press down this side. You press down that side. We'll see who wins.
Okay, ready?
Yeah.
1, 2, 3, go. Oh, wow, that was really tough. Why was that so hard?
Well, Phil, I'm just really strong.
Wait a minute. My turn. Okay, 1, 2, 3, go. Yeah! See, pushing down on this one is way easier. You wouldn't think that the small syringe would be easier. Why is that?
The reason for it is that you have to push this one down a lot farther than you have to push this one down.
Let's see.
See how far this one goes, and this one's barely moving?
This one travels much more. This is how we can exchange a little bit of force over a long distance.
That's right.
To a little bit of distance at a lot of force.
That's exactly right.
Just like the lever, it's a mechanical advantage. But in this case, it's hydraulic advantage.
That's right.
Chris and I push down on small syringes, which gives us more force on our larger syringes. Our crusher was ready to go. Ooh, how about an orange? 1, 2, 3. We squeeze down and... Then we tried a walnut. Are you allergic to nuts?
I am not.
1, 2, 3. When we tried a golf ball, we reached the limit of what our plastic syringes and our hands could do. We need to come up with a stronger, more awesome crushing machine using hydraulics.
That's right. I have some ideas.
Okay, good. We can use metal.
We can use metal.
And we can
go bigger as well.
Ew, this water is gross, but I'm gonna drink this water. Why? Well, because of science. No, but I'm not gonna drink the water like this. First, I'm gonna use the power of science to help me clean it. How? By using gravel. Gravel, yes, gravel. So, say I've got some dirty water, and there are particles floating in that water. Large particles, your rocks, your wood. These styrofoam bits will act as the large particles. You pour it into the gravel, and the large particles get filtered out. See? Nothing but clean, clean water. Yeah, I know what you're thinking, Phil, that's not really clean yet. That's because we haven't done step 2, sand. Sand? Yes, sand. Let's say that these plastic beads are small particles. That filters out the tinier stuff. There, huh? Clean, right? No, it's not very clean. So, we filter the water in the next step with charcoal. What? Charcoal? Yes, charcoal. Charcoal works just like gravel and sand, except on a microscopic scale. Say these bits are tiny particles you can't even see. The charcoal catches these like the sand and gravel caught the larger particles. This is called a gravel, sand, and charcoal filter. The gravel catches the big particles, the sand the smaller ones, and the charcoal the microscopic ones. These kinds of filters are used all over the world to clean drinking water. Ah. Delicious. Science. This is ferrofluid. It is ferromagnetic, which means it's attracted to magnets. And I know what you're thinking. You're thinking, it's not that interesting. Well, watch as I put it next to this magnet. Very interesting. And because it's a liquid, it behaves in very interesting ways. Watch this. Unlike most things ferromagnetic, like paper clips or iron filings, ferrofluid is a liquid, which means it behaves in a unique way. The spikes it creates are following the magnetic field lines of the magnet. You can see the magnetic field in 3D. It's even more impressive when we max it out. This is ferrofluid outside of a glass jar. Now, it's sitting in a pool around this electromagnet, and this is a dial which I can use to change the voltage of the electromagnet, making the magnet stronger. Watch this. Changing the current going to the spiral in the middle turns it into a magnet. The more current I put in, the stronger that magnet becomes, allowing the ferrofluid to climb the spiral to the top. And remember, even though it looks all spiky, it's still a liquid. I will demonstrate with my plastic spoon. And watch this. When I turn the magnet off, it stops being spiky. Turn it on. Turn it off. Science.
The Wizard Academy. All you have to do is demonstrate true magic. And you will be granted entry.
Well, Fuzzix, who is the next applicant for the Wizard Academy?
Overwhelmo. Indeed, it is I, Overwhelmo. And prepare to be overwhelmed. Would you be flabbergastified if I balanced this coin on its end?
Not really, no.
But would you be impressed if I was to balance this coin on top of this coin?
Possibly.
Prepare to be flustered and stupefied. Stupeflustered as I balance 3 coins on their ends on top of this glass.
Well, that certainly would seem like magic. Let us see.
Okay. No pressure, Overwhelmo. You can do this.
And now, I say, a magic word.
A magic word! Ha 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 ha! And now you must let me into your academy.
Wait. What's under the cloth?
What cloth? This cloth? Nothing. Oh!
Is that a magnet?
This? No!
The pull of the magnet is what's keeping those coins up. The magnet is just strong enough to keep the coins from falling.
No, this is set dressing. It's just...
It was a good trick, but it's science, not magic.
Well, yes. And you will see! You will see! I will be back! I, Overwhelmo, will return! And I will do such magic that you will need extra socks. Because I will knock them off! With my magic, you will need at least 2 pairs of socks. Maybe 3 pairs of socks.
We can still see you!
No, you can't!
As you may have already guessed, today is about friction, and here's a really easy friction experiment you can do at home. All you need is a piece of wood. You don't need the frame, and you don't have to do anything fancy to it. Just put one end up on a couch or a coffee table and make a nice ramp. Then you want something to slide down that ramp, and I like to use a piece of wood. Now check it out. Wood ramp, wood block. The friction is so much that the wood slides to there. Now what I like to do is take a little flag and mark the results. Recording the results is good science. Now here's where it gets fun. Get another surface and attach it to the wood, like carpet and wood. Let's see how far this goes. Not as good. All right, record the results. Cardboard. Ooh, nicely done, cardboard. Foam. And this wood has been waxed, like on a floor wax, which makes it nice and slippery. Let's see how that does. Ooh. And now the ultimate ice attached to wood. This is actually harder to do than I thought. All right, let's try it out. Ice! The clear winner. Not a big surprise right there. And get this, once you've done all of that, you can change the surface of the ramp. You can go to waxed wood, carpet, boom, cardboard. Well, well, yeah, you get the idea. Record all the results, compare them, and there you go. Friction ramp experiment. And that's what we're gonna be maxing out today. So come on, let's go. This is a string. You can pull a string, but you can't push a string. Well, you can. You can push a string. You really can. Okay, quit it. Quit it. This little contraption works sort of like a baseball pitching machine, but in miniature. See, there are two motors here, and the wheels spin together to shoot things out this way. Things like this craft stick. Watch this. Whoa! Let's watch that again. Whoa! But now, watch as I put a large loop of string through. What? Pushing string. How does this happen? Hello?
I don't suppose it's the Magnus effect?
No, it's not the Magnus effect.
No, it's all right. I'll be in my lair if you need me.
Okay, right. Bye. Right, where was I?
I believe you were at, the reason why this works is...
Right, pushing string. How does this happen? It's all because of inertia. Check it out. The wheels are pushing the string through fast. It's got some weight, and it's got some speed, which means it has some inertia. So when it goes this way, it wants to keep going this way. But it goes all the way to the end, and then, because it's a loop, gets sucked back in this way, which means all of this inertia, you can sort of overcome gravity. Pushing string, science. Today we're combining two different chemicals to create a reaction. Sometimes chemicals can combine in a way that makes them very different from how they started out. For example, this is sodium, or Na on the periodic table. Now, the sodium tablets are in mineral oil because sodium reacts very strongly with water, even the water in the air, or especially the water in my skin. Watch what happens when I drop a sodium tablet into this beaker of water. Very cool and very dangerous.
And this is chlorine, or Cl on the periodic table. Chlorine gas is very poisonous. So,
So, what happens if we combine these two deadly substances? Do we create some sort of super poison? Something more deadly than anything else known to science that causes fear and chaos in chemistry labs all over the land? No, we create salt. Good old normal table salt. These two substances combine to make NaCl, salt. Something completely and totally safe. Chemistry. This is our control pumpkin. A control in science means a version you don't experiment on, so you can compare the results of your experiment. So this is what a pumpkin does when dropped with nothing to cushion the fall. Jenna and I really have our work cut out for us because a pumpkin has a lot more mass than an egg, which means it's going to be much harder to stop once it's moving. So now all we have to do is come up with a couple ideas to stop that from happening.
All right, let's do it.
Science. Yeah. You want the best material around? Well, you come to the right place. I've got them all. I got you flubberoid, magnoplex, flexoweed, pastotherm, blooperfoam. You need hydrogelatinous substrate? I got it. But you know, all those fancy materials are nothing compared to the good old-fashioned spider web. Huh? Hey, where's Gary? Ramona, Gary got away again. You know, people ask me, Sal, is it true spider webs are stronger than steel? And I tell them, it depends. When you look at a rope or a thread or a fiber, you talk about its tensile strength or its ability to withstand force before breaking. But you're comparing different things, so you have to compare them by thickness. So if you're comparing a steel cable to a spider web of the same thickness, then yes, steel is stronger. But spider web is 6 times lighter than steel. So if you are measuring strength to weight, spider web wins every time. Gary! So why don't we build more things with spider web? Well, for one thing, it's sticky and difficult to work with. Almost finished knitting this spider web sweater. It's only gonna take me about 80 more hours. And it's not easy to train spiders. Okay, Steven, one long, non-sticky thread and you get a cookie, okay? And, hey, where's Marco? And Petunia. Huh? But no need to train spiders now because modern science has surpassed the spider web. Enter carbon nanotubes. Huh? This thread doesn't look like much, but it is made of tiny little tubes made of carbon atoms. Think of them like a straw, but a really long straw. Carbon nanotubes are incredibly light and strong. Remember when we compared strength to weight? Well, steel is heavy. Spider web is about 6 times stronger by weight, and carbon nanotube is about 50 times stronger than that. That's so great. So why aren't we making everything out of carbon nanotubes? I'm gonna knit a carbon nanotube sweater. Well, first we have to make them cheaply enough to be affordable. There you go. One carbon nanotube sweater. $480,000. But material scientists all over the world are hard at work trying to find ways to make carbon nanotubes faster and cheaper. And soon, they'll be everywhere. And then spiders can go back to spinning their webs in peace. There you are, Gary. Where's everybody else? Well, Petunia and Marco and... What do you mean they're in my jacket? Now it is time to talk about an amazing natural polymer. It is hagfish slime? Ugh. Still, well, hagfish, that's probably just an unfortunate name for the fish. I'm sure the fish itself doesn't. Ugh. Okay, so hagfish makes slime, apparently. When a hagfish is attacked by something that wants to eat it, like a shark or an eel, it secretes a tiny bit of a natural polymer. That's this little white bit right here at the end of this test tube. Now, it doesn't look like much right now, but it reacts with seawater. Watch this. Hagfish slime is very interesting to scientists because you start with just a tiny little bit and add seawater, and suddenly you have a lot of slime. Whoa. This stuff is actually pretty cool. Hagfish slime is a natural polymer. It's made just the same as the other polymers out of long chains of molecules, but it's naturally produced by a living organism. And because it's naturally produced, that means it's biodegradable. Hagfish slime. It's pretty cool after all. Foam. Foam. Foam! How can they all be foam? Well, foam usually means something to do with bubbles. There's all kinds of solid foams out there, and they can be squishy or not squishy. And they're usually light. Air is an insulator. That means it does not conduct heat or cold very well. You see, I cannot tell this ice is cold until I get my finger really close to it. Yeah, there it is. There, I feel it. And because foam is full of air bubbles, it makes a great insulator. That's why we make coolers out of foam. So what's the best, most advanced foam out there? It's this. It's called aerogel, and it's 98.2% air. It is super light because it's mostly air, and it's a great insulator because it's mostly air. It's great to pack things in as well, and NASA uses it on the Mars rover and in spacesuits because it's such a good insulator. Cool. Or not cool, because, you know, it's an insulator, so it would protect from the cool. Inertia. What is it? Well, it's directly related to Newton's first law of motion. An object in motion tends to stay in motion, an object at rest tends to stay at rest. Let's do an experiment. Here is an object. Right now, it's at rest. You might think that means it has no inertia, but that's not true. Inertia just means an object's tendency to keep doing what it is doing. Right now, it's doing nothing. But if I wanted to overcome its inertia, I would have to put energy in. And now that I have, it is moving on its own. It has inertia. If I wanted to stop it, I would have to overcome its inertia, its tendency to keep moving. There. I went exactly that far. Now, let's max it out. I'm adding these weights to the cart. Now it has a lot more mass, which means it has a lot more inertia and its tendency to do nothing. But this time it has a lot more inertia. If I wanted to get it going the same speed as before, I'd have to put in a lot more effort. There, now it's going the same speed as before, but now it has way more inertia, so stopping it will be harder. So there you go, inertia. A thing's tendency to stay moving or stay still, and the more mass, the more inertia. Dear Phil, I can't believe you did a whole episode on boat propulsion and you didn't use the greatest thing out there for making a boat move, a propeller. Sincerely, a fan. Well, let's talk about propellers. Oh. Good thing this is fan mail. Get it? Because it's a fan? Yeah, anyway. A fan pushes air just like a boat propeller pushes water. They're both fluids and they behave in the same way. Now, if you look closely at a fan, it's curved on the blades. The air or water is caught under at this side and then it's pushed out on the curve to make it go that way. And the faster it spins, the better it works. Now, this is a propeller-powered boat. And what you do is wind up the propeller. I have an elastic band here to store the amount of energy I put in. And then you put it in the water, the propeller spins, and the boat goes forwards. It's being propelled by the propeller. That's why you call it that. Awesome, right? Well, now we'll max it out. This is a drill. It spins. And this is a propeller, and when you put it in the water and spin it, it provides thrust. So let's try it out. Whoa! Remember not to try this at home. I am a trained professional. This is a very small propeller. Let's compare. This is a super maxed out propeller. Whoa, okay, let's try it out. Whoa! The larger a propeller is, the more energy you need to turn it, and the more propulsion you get out. Whoa. This is Newton's cradle, and it's a really cool toy that demonstrates all kinds of laws of motion, including Newton's third law. What you do is you pull this one ball out, and when it hits these balls, they exert force on that ball to make it stop moving, but it exerts force on these balls, which travels through the balls and makes this one on the end fly out, like that. Now, there's a lot going on here, but you can really see how the force is equal that you put in and you get out if you use two balls. I swing two balls up, and two balls go out that side. Isn't that cool? Now, it wouldn't be science max unless we maxed it out, so come on. Whoa, okay. This is one we built out of bowling balls. Bowling balls. Bowling balls. Instead of smaller balls, and I think it's gonna work the same way. Let's find out. You throw one out, and
And yeah, it works the same. Okay, now let's try it with 2 balls. Okay, ready? Wait. And 2 balls, throw them out. And 2 balls on that side. All right, so there you have it. Newton's third law. Oh.
Newton's third law. For every action, there is an equal and opposite reaction.
Greetings, Science Maximites. My name is Phil, and it's moving day today on Science Max Experiments at Large. Let's see, where do I put this? This is probably a good spot. Today, we are moving air. You probably don't think that moving air will have a huge effect, but you'd be surprised what you can do by just moving air. But don't worry, we're not just gonna move the air around in boxes. We are going to build a rocket! And this rocket uses the science of stomping on something with your foot. This is a stomp rocket, and it works by stomping on this plastic bottle, and air shoots through this tube and pushes the rocket up into the sky. And here is how you can build one of your very own. And remember, if I go too fast, don't worry. All of the steps are on the website, so you can follow along at your own speed. All you need is a 2-liter plastic bottle, 3 kinds of tape: electrical tape, duct tape, and science tape. Science tape is just the same as invisible tape, but I use this kind of tape for science. Then you want some plumber's tubing and some construction paper to make your actual rocket. First, you want to take your plumber's tubing and cut it into 3 lengths. And when I say you, I mean an adult, because you need to use a saw. So you saw it up into a long piece, a short piece, and an elbow piece. We want to make a long tube at the top, and then we also want to make a tube at the bottom so we can attach our 2-liter bottle to. And there we go. Ta-da! Ready to go. But of course, it doesn't stay up, so we have to attach it to a base. And it will look like this. And you see, it's been attached with duct tape here, and I've used electrical tape, and I've wrapped that part around there. Now, building the rocket. Wrap the paper around the tube and tape it with your science tape. Tape the top closed so no air escapes. Then cut a semicircle to make the nose cone, and 3 hoops for thrusters, and tape them to the bottom. There you go. The rocket fits on the tube just like that, and when you stomp on this bottle, it launches. But here's the most important part. The one most important rule of launching rockets. You shoot rockets outside. Come on. Once you get outside to a nice open area, and you bring your safety glasses with you, all you need to do to make the stomp rocket work is, of course, stomp on it. You ready? Here we go. 3, 2, 1. Whoa! Did you see that? That was amazing. Here is something mind-bending you can do with pulleys. These buckets are attached to the table through a pulley. There's nothing holding this table up except for the weight of the buckets pushing down on the table. So if I took the buckets off the table, the weight of the buckets pulls the table up. But because the buckets are on the table, everything is in balance. Mind-bending, right? Okay, wait, it gets better. If I took a weight and I put it on the table, the weight of the buckets isn't enough to keep the table up. So I have to add more weight to the buckets, so the buckets pull the table up. Whoa. And there you have it. It's weird, it's mind-bending, it's science.
This is a pendulum. It's a weight that swings. It swings back and forth. Pendulums are pretty simple. It swings back and forth. Predicting the path of a pendulum, pretty simple. It's gonna swing back and forth. But wait, as I make it so much more complex by adding a pendulum. Now I've got a pendulum down here, and that one swings back and forth, and I've got a pendulum up here that swings back and forth. What will happen to this part of the pendulum when I let it go? Can you predict? Let's find out. This is a double pendulum, and predicting the path of a double pendulum is really difficult. It's still simple physics, but because there's a moving part attached to a moving part, it makes it way more complex. So, the question is, can we max it out even more? Of course we can. These are chaos pendulums. This one's a lever, and it's got another lever on the end. Whoa, and this one here is a perfectly balanced lever, and it's got a pendulum on either side. Whoa. Whoa. Scientists and engineers have always said that the more moving parts something has, the more complex they are. Science. Here's another small experiment you can do with inertia. Take a stack of checkers, or game pieces like I have here. Oh, or coins. Coins work really well. And a ruler, or something else that's flat. This is the kind of stick they give you at the hardware store to stir your paint with. Now, you can knock checkers out of the middle of the stack without the stack falling over, if you're very careful. You see, the friction of the checkers leaving the middle of the stack won't be enough to overcome the inertia of the rest of the checkers. Ready? Now, let's max it out. Oh, I have these pizza boxes, and they should work the same way. You see, you get a stack, and don't worry, I've already eaten all the pizza. And I put them on there like that, and now I need a ruler. And what I've got is this cricket bat. You see, it's got a nice flat edge, just like the ruler. Now, if this works right, I can hit it hard enough to knock out just 1 or 2 pizza boxes, and the rest of the stack should stay. Here we go, ready? Science! Awesome. And there you have it. Newton's first law. An object at rest tends to stay at rest, and an object in motion tends to stay in motion. An object in motion tends to stay in motion. Usually there's a sign that kind of... Bernoulli's theorem states that faster moving air has lower pressure than slower moving air. You can demonstrate this yourself with a ping pong ball and a hairdryer. You put the ping pong ball on the stream of air from the hairdryer, and because it's moving quickly, it has lower pressure than the air around it. So the low pressure air works sort of like a force field, and you can defy gravity with your floating ping pong ball. Awesome! But of course, this is Science Max Experiments at Large, so we have to max it out with a giant hairdryer and a giant ping pong ball. Sorry, I said science! You probably couldn't hear me because of the... Tornadoes are giant weather systems that cause the air to go around and around. Tornadoes can be pretty dangerous, but they don't happen that often. Here's how you can make your own small pet tornado you can play with at home. Because air and water behave similarly, we can make a water tornado. You spin it around, get it going, and ta-da! Your very own pet tornado. Here's how you do it. You take 2 2-liter plastic bottles and fill one with water and some blue food coloring, is what I like to do. And then tape the mouths of the bottles together. You might need an adult to help you with this because you want to make sure the bottles are perfectly aligned. Then flip it over, spin it around to get it going, and voila, your very own pet tornado. Awesome. And now we're gonna max it out with a giant tornado chamber. If I was to drop this light basketball and this heavy workout ball at the same time, which do you think will hit the ground first? Let's find out. They landed at the same time. That's because everything falls at the same rate. It doesn't matter how heavy or how light something is. Until things are falling fast enough that air friction or drag starts to play a factor. Soon, things reach their top speed. This top speed is called terminal velocity. It means I could throw this basketball from an airplane, and it might not be going any faster than if I threw it from, say, 10 stories up. I'm gonna find out what the terminal velocity is for both of these objects when we max this out. Ninja science roll! Here's how terminal velocity works. Everything falls at the same rate, going faster as gravity pulls it down. But when things start going so fast that just pushing through the air at that speed creates as much force as the pull of gravity, things reach a top speed and they won't go any faster. How heavy something is and how much air it pushes both play a factor in its top speed. And that top speed is called terminal velocity.
How cool is that? I'm in iFly Toronto. This is a giant wind tunnel, and they've got the wind going fast enough that they can't fall any faster. It's the terminal velocity for a human being. I'm gonna take our weighted ball and our basketball and place them both here in the wind chamber.
This is the control panel, which is what they use to control the wind speed inside the chamber. And this is Derek, who's gonna be operating it. And that is Mike and Greg, and they're inside the chamber. All right, let's fire it up.
All right, firing it up.
35, 58, nothing happening yet.
This number here is the one we're looking at to see how fast the air is moving.
86, something's starting to happen. Oh, 89, wind speed of basketball, 89 kilometers an hour. At 89 kilometers per hour, the wind is going fast enough that the friction of the wind and the pull of gravity balance out, making the basketball float. This means you could throw a basketball out of an airplane and it would never go any faster than 89 kilometers per hour.
All right, let's keep increasing the speed. 106, 124 kilometers an hour, 140, 150. Oh, 166, almost. 172, whoa. Wind speed of the heavy red ball, 173 kilometers an hour.
Because the red ball is heavier than the basketball, we need a lot more wind speed to counteract the force of gravity before they cancel out and the ball floats. Here's something else that's going on that's cool. Mike is flying, but Greg is not. That's because Mike is lying down, which means he's catching a lot more wind than Greg is, who's standing straight. If Mike stays lying down, his terminal velocity is the same as the red ball, 173 kilometers per hour. But Greg's velocity would have to be a lot faster.
And that's science! All right, pliers, battery, copper wire. Now, if you've already done the electromagnet experiment, here's another experiment that uses all the same materials, plus these. Ha! Neodymium magnets, some of the strongest magnets you can get. So, here's what you need.
A battery, some neodymium magnets the same diameter as your battery, copper wire, and some pliers.
So here's what you do. First thing is you put the batteries and the magnets together, like that. Then what you want to do is bend the wire so it's touching the top of the battery and goes around the battery and then touches the magnets at the bottom. Here's what that might look like. I say might because you can do any shape you want. I've made a coil here. And if you put it over the battery, you'll see it only touches the very top of the battery and the magnets at the bottom. And if I let it go, it spins. It's a homopolar motor. What happens is the battery sends an electric current through the copper wire, and that turns it into an electromagnet, which is attracted to the magnets at the bottom, and it spins. So, now, let's max it out. Aha! A D-cell battery, which is larger and, of course, larger neodymium magnets. And you do the same thing. Make a coil that only touches the battery at the top and at the magnet, and ha-ha! It spins! Maxed out homopolar motor. But don't worry, this is not the biggest size we're gonna do. Come on. Maxed out homopolar motor. I have 27 D-cell batteries, a giant copper tube, and a neodymium magnet. So I'm just gonna, and then we get rid of that. Put this down. Okay, so the first thing I do is attach the neodymium magnet to the batteries. And I've got all the batteries taped together here so they'll sort of stand up like this. Huh? Giant stack of D-cell batteries. Okay, now what I do is I take the copper coil. I need to get, okay, hold on. I got this. I just need to get the copper quality. I did it. Okay, so I take the copper and I put it on top of the D-cell batteries like this, and then I let it go. Let it go. Nope, whoa. Homopolar motor. Okay, so that didn't work. But that's okay. I like it when it doesn't work, because that's science. It's not science if it works perfectly every time. I mean, you gotta have some room for improvement. This is water. Now, it's ice water. Science! Okay, no, that's not the science part. Here's something you can do at home. Get some ice water and a way to time yourself and stick your hand in the ice water. It's a little hard to stick your hand in ice water for a long period of time because after a while, it starts to hurt. But don't worry, the pain that you're feeling isn't actually because you're damaging anything. It's just your body's way to tell you that you need to take your hand out of the cold water. Yeah, you usually can't do it for very long. But some animals, like seals and whales, they live in ice water all the time. They live in the Arctic, so how do they do it? One word, blubber. Blubber is a layer of fat that protects you from the cold, or protects the seal and a whale. We don't have blubber, but we are today gonna have some blubber, because we're gonna make a blubber glove. Blubber glove, I love saying that. Here's how we do it. First, we want blubber. Okay, this isn't blubber, this is lard, which is actually animal fat. You can use lard, you can use margarine or butter or shortening, anything with a lot of fat in it. And remember, this is messy, so definitely get an adult to help you. So we've got our lard, and we need a bag. So what you're gonna do is you're gonna take a scoopful of lard, like this. And you're gonna put it in the bag, like so. Like that. There we go. And then you're gonna start smoothing out the blubber or the lard like this. Because what you wanna do is have a nice, thin layer all the way around. See? Starting to work? Yeah. Then seal the bag and tape the edges. A square of blubber. Then do it again. Here I have 2 bags of blubber, and I've taped all the way around the outside. So I have a blubber glove. Check it out. So let's try it out. I stick the blubber glove in the ice water. It's completely working. It is not even cold. The blubber is completely protecting my hand from the ice water. I'm not even remotely cold at all. That is very fun. So, try it yourself. A blubber glove. Now, how do we max out a blubber glove? Watch. Water, ice water. I know for a fact that I wouldn't last more than 10 seconds in here without my blubber suit. I'm gonna make an entire outfit of blubber. I've got them in large plastic bags, and I'm going to get completely suited up in blubber with the help of Trevor and Stephanie. Okay, guys, suit me up. It's very heavy. Let's just go like this. Oh, okay. Time to cut back on the cookies. All right, let's do it. All right. Blubber suit, go! Okay. Oh, here we go. In. Okay, so far. Oh. The legs are warm. And. Oh! Blubber suit! Ha ha ha! I am in seals! Actually, here I am in the ice, and I don't feel too bad. Blubber suit works! Ah! Blubber suit's refreshing, actually. You just sit back and chill out. Well, there you go. Blubber suit success. Seals and whales are able to stay in ice water for their whole lives because they have protective layers of blubber just like I do. Okay, so now all I have to do is get out.
Blubber suit! Oh no! My blubber is leaking! Ah, I've sprung a leak! My blubber! Oh, my precious blubber! No, what a world! Dear Phil, I can't believe you did a whole episode on boat propulsion and you didn't use the greatest thing out there for making a boat move, a propeller. Sincerely, a fan. Well, let's talk about propellers. Oh. Good thing this is fan mail. Get it? Because it's a fan? Yeah, anyway. A fan pushes air just like a boat propeller pushes water. They're both fluids and they behave in the same way. Now, if you look closely at a fan, it's curved on the blades. The air or water is caught under at this side and then it's pushed out on the curve to make it go that way. And the faster it spins, the better it works. Now, this is a propeller-powered boat. And what you do is wind up the propeller. I have an elastic band here to store the amount of energy I put in. And then you put it in the water, the propeller spins, and the boat goes forwards. It's being propelled by the propeller. That's why you call it that. Oh, hello there. Here's a fun science experiment you can do with science and friction together. Take two books, put them on top of each other, and pull them apart. Ooh, not too much friction. But if you take the books and you interleave some of the pages, maybe 3 or 4 parts, and try it again, pull them apart, they're a little harder to pull apart. That's because the friction for more pages touching each other actually starts to add up. So, what if we were to take 2 books with a lot of pages and very carefully and meticulously take each page individually, one at a time, and overlay each one and go back and forth? These are 2 books completely shuffled together. The elastic band is actually just to hold the covers together. All right. So, now the friction between all of these pages, when I try to pull it apart, makes it pretty much impossible. Now, there's 2 things going on here. First of all, when you start to pull the books apart, the pages start to stick together because they squeeze together, because you're pulling and they're squeezing. And the fact that there's so many pages sticking together, the friction builds up to a degree that is actually very impressive. But don't take my word for it. Let's max it out. Here is another 2 books, elastic just to hold the covers. This one clamped to the wall, and I'm gonna pull on this one. Science! Still don't believe me? Well, let's max it out some more. This is a climbing frog. Why does he climb? Because of science. I pull on this rope, and then I pull on that rope, and I pull on that rope, and he climbs up the ropes. And why? Well, because of friction. The secret is 2 straws. The straws are pointed away from each other at the bottom. This allows it to climb thanks to friction. Take a closer look. When I pull on one string, it pulls straight, which makes the frog pivot. That string slips through the straw because there's not a lot of friction, but there's lots of friction on the other side because of the angle. So one side of the string goes down, which makes the other go up, which means the frog goes up with it, all thanks to friction. So now, let's max it out. This is a super maxed out climbing frog. Just like the small version, I have a rope going through 2 tubes. I pull on one rope and the other holds on by friction. Then I switch. And it does work. It's just a lot harder to pull on the ropes, but it totally works. Whoa, careful. Whoa. There, and then this one, and then that one, and then that one. Yeah! A giant climbing frog! Whoa. Here's another way to defy gravity using friction. Get a plastic water bottle and fill it with rice.
Take 2.
So get a plastic water bottle and fill it with rice using a funnel. Then take a shish kebab skewer and stick it into the bottle and nothing happens. But if you tap the bottle down, the rice starts to pack in a little bit better. See how the level of rice is lower? Which means you can add more rice. Pack it down even more. And you can even use something the same diameter as the mouth of the bottle, like, say, a highlighter. And make sure all the rice is as packed in as you can get it. There. Now the rice is really packed in there. And when I stick the shish kebab skewer in, the friction between the pieces of rice and this wood is enough to lift the bottle using nothing but friction. Now, let's max it out. I filled this 20-liter water cooler jug full of rice, and it's really heavy. I wanted to see if I could lift it using nothing but friction and this dowel, which is just a round piece of wood. All right, here we go. Ah, science! I'd max it out even more, but I don't think I could lift anymore. Batteries are great at storing energy. They store electricity. Batteries? But if you're like me and you have a whole bunch of batteries and you don't remember which are the good ones and which are the dead ones, there's a trick that you can use to find out. Get a frying pan or a brick or concrete floor or something else that's very, very hard and an adult's permission. Here's the secret. Dead batteries will bounce and batteries that still have some life in them won't. Watch. Good battery. Dead battery. Now, it's a little hard to see, but listen. 1 hit, 2 hits. Here's what's going on. See, batteries store electricity in the form of a gel, sort of like modeling clay. This is modeling clay, fresh from the fields, where the mine, wherever modeling clay comes from. And this is modeling clay I've left out for about 5 days, so it's all dried up and hard. Now, when modeling clay is new, it's all wet and soft, and when you drop it, it doesn't bounce very well. I've left this piece of modeling clay out to dry for about 5 days. Now it's all dried up and old, and it bounces. New, old. So, same thing with the battery. Good batteries won't bounce, and bad batteries will. Science. When water is going fast, it has a lot of force. This is a power washer. It's made for cleaning concrete and wooden decks, but it doesn't use soap and it doesn't use heat. It only uses the power of water. Let's try it out. The power washer creates a stream of water that is moving really fast. It has the force to clean concrete, strip the paint, or even the Science Max logo off wood. But how do I max out the power washer? What's the most ultimate use I can think of? Power washer pumpkin carving! The power of the pressure washer creates a stream of water strong enough to make short work of my pumpkin. Power washers may only shoot water, but they can be dangerous, so don't try this at home. Yeah, science! This is a house of cards, and if you've never built a house of cards, you should definitely try. Try, because it's not easy. What you need to do is you need to make triangles with the cards. If you do it just right, they'll stay up. Then you take another pair of cards, like that. You take another card and you put it on top. And it stays up. Keep on building by making triangles and putting another card across the top like a roof. Then, when you're ready, you can start to make a second layer. It takes a lot of patience to make a house of cards. But with enough patience and really steady hands, you might be able to finish it. There we go. Ha-ha, a house of cards. Now, let's max it out. Shh, backing away slowly. Backing away slowly. To build our maxed out card house, the Science Max build team and I used large pieces of foam insulation, which were super light and easy to work with. Once we set up the first layer, we needed to bring in a scissor lift so we could keep building the next layers. By the time we got to the top, our card house was 10 meters tall. Yeah! Giant house of cards! And now that I've built a giant house of cards, what do I do with it? I knock it down. Science! I'm gonna build it again. All sound is vibration, but it's really hard to learn about that vibration if you can't see it. I mean, sound is invisible, right? Well, here's a way that you can make sound visible. All you need is some plastic wrap and salt and a bowl, just a regular bowl, and an elastic, like this. So what you do is you take the plastic wrap and cut off a piece just large enough to fit over the bowl, and then use the elastic to wrap around the bowl to keep the plastic tight. Pour some salt on the bowl, and then watch this. Hello, vibrating salt. The plastic wrap is stretched tight over the bowl, making it like a drum. A drum that's very sensitive to sound vibrations. Your ear works the same way. That's why we call it an ear drum. The vibrations from my voice make the plastic wrap vibrate, and that makes the salt dance. But there's more. Let's max this out. This is a Chladni plate, and what it is just a piece of metal on a platform that vibrates up and down to a frequency which I can program with this dial here. And when the sound waves vibrate the plate, they can interact in ways that make the sand form interesting patterns. Take a look. The sounds I'm generating vibrate the plate, make it move like a wave. But when the vibrations reach the edge of the plate, they bounce back and interact with the other waves going the other way. The way these waves interact at different notes is what causes the sand to make these different shapes. So this is great, but you know what? We can max it out even more. Maxing it out even more. Okay, that's about as much as I can take of that. Whoa. Here's a fun experiment you can try. If you have something heavy, like this glass of water, and you put it on a piece of paper, you can experiment with inertia. If you move the paper slowly, the glass moves with the paper, because the friction between the paper and the glass is enough to overcome the inertia of the glass. But if you move the paper quickly, the friction is not enough to overcome the inertia, and the glass stays put. And now, let's max it out. Okay, let's do it. All right, now you might be tempted to try this at home, and you can, but please, for me, promise that you'll let an adult know you're about to do this. And don't use breakable plates. Use plastic plates, because this will take a couple times of practicing before you get it right. Put something on the plastic plates, because the heavier they are, the better it will work. All right. Did I mention not to do this at home unless an adult knows you're doing it? I cannot stress that enough. Okay, deal? All right, deal. Here we go. And there you go. Newton's first law. Thank you. If you want to build a block tower, you might think the fastest way to do it is just by building a single stack of blocks. But science may have a few things to say about that, and those things would be no. Let's try it with books. The books are much wider than the blocks, so that will give me a wider base, right? But it's all about the center of mass. You compare how wide it is to how tall it is. Right now, it's pretty wide and it's not that tall, so the center of mass might be around here. But if you go high enough, how high it is compared to how wide it is changes a lot. It's getting higher, but not any wider. The center of mass is probably right around there somewhere, which means it's gonna be really hard to balance that. Whoa, careful, almost. I can do a little bit more, I bet. Oh, careful, careful. Whoa. It'll only get so tall. So there you go. You can never stack a single stack of anything very high. But just in case you don't believe me, let's max it out. Oh, careful. Now it's time to see how high, how high I can make a single stack of boxes. Okay, and whoa, 6 boxes! 6 boxes! 6 boxes! Whoa! Can he go as high as 12? Let us find out if I can go as high. Apparently not. Can he go as high as 11? Can he go as high as 11 boxes? Let's find out. Oh, careful, careful, careful. And a single stack of boxes! Huh. Okay, well, like I said, you can't stack a single stack of things too high, because it will fall. Science! 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 Did you know it's easier to float in salt water, like in the ocean, than it is in fresh water, like a lake or a pool? That's because not all liquids are created equal. They have different densities. This is fresh water, or it doesn't have anything in it. And this is sugar. If I was to put 1 scoop of sugar in this water and stir it around until it dissolves, now this liquid is more dense than before I put the sugar in. Here's an experiment you can do at home using liquid density. This glass just has regular water with yellow food coloring in it. This glass, green food coloring and ½ a cup of sugar in it. This one has a full cup of sugar in it, and this one has 2 cups of sugar in it. Now, when you do this at home, you'll definitely want an adult to help you because you have to heat the water if you want to dissolve that much sugar in 1 glass of water. I'm gonna put them all in 1 container. You can do this at home, and when you do, I suggest you use a very small container because you have to be very careful when you put the layers in. You can use a turkey baster or a straw. When you put your finger on top, the air pressure will hold the liquid in and you can just drop it in. But these kind of take some time, so I'm going to use the syringe of science. I'm gonna use the most dense liquid first because that's the one that's gonna want to be on the bottom. I carefully put it on the bottom of the container. The next layer, be very careful, and you'll see that the red and the blue aren't mixing because they have different densities. The blue is heavier than the red. We'll add the green, and you can see even when it drips into the red, it comes back up to the top because the green liquid isn't as dense as the red liquid, and the denser liquids push the lighter liquid up. And now we're gonna add the yellow, which of course has no sugar in it at all. And there you go. All the layers stay separate. If you put it on a light, you can really see it. Liquid densities. Now, let's max it out. Ta-da! The longest length of liquid layers. 12 liquids, all organized by density. Starting from the bottom, we have honey, corn syrup, chocolate syrup, maple syrup, dish soap, whole milk, water, dyed blue, vegetable oil, extra virgin olive oil, rubbing alcohol, baby oil, and lamp oil. Liquid density. I really want to mix it up, but it took me a long time to make this, so I'm not going to. If you attach something ferromagnetic like this washer to a magnet, not only does it stick, but the magnetic field travels down the metal, making it a magnet too, which means you can stick more and more things to each other, and they will continue to stick until
you run out of magnetic field. You can do this yourself at home with anything ferromagnetic. Paper clips work pretty well, or washers like I have, or screws or bolts, and they'll continue to stick to each other as long as the magnetic field is strong enough. You can see it's getting pretty weak here. And they'll all stay magnetized as long as the first one is still attached to the magnet. But if you want to go even further, all you need to do is keep adding more magnets to reinforce the magnetic field. I've got a few here, like this. Get the chain started, like that. And then I've got a magnet attached to this washer, so it will keep the magnetic field strong. And I continue to add one magnet, one washer, and we'll just see how far I can go. You can even sculpt it a little bit. Look at that. And then at the end, a whole bunch of paper clips. Eventually, the weight will make it fall off, but it's a lot of fun to play with magnets and make art. Speaking of art you can make with magnets, you can also make sculptures. When everything sticks to everything else, you can make some pretty fancy designs. This is a rare earth magnet, a very strong one, and a bunch of nuts that I've gotten. And this one here is an electromagnet, but electromagnets are a little different because they need an electric current to work. Check this out. This is sort of a magnet dude with crazy hair. There's an earth magnet here, and this is a giant screw, and these are some metal bits, and then I've got two more magnets at the top here to hold on his crazy wire hair. He's got crazy wire hair because he's crazy magnet dude. Now, of course, we couldn't just talk about magnetic sculptures without maxing it out, so let's max it out. This is a bunch of scrap metal from leftover experiments, and I've got a bunch of rare earth magnets, and now I'm gonna max out a magnet sculpture. Let's see. There you go, a maxed out magnet me. I made this guy out of metal pipes with earth magnets in between, and these are his arms attached, of course, with magnets. His hand, his little metal pieces attached with magnet. Steel wool for the hair, and of course, hat, non-magnetic. All right, here we go, ready? Want to see a magic trick? Simple copper tube. Drop things through it. Nothing unusual happens, but watch when I drop a magnet through. What? It's not magic, it's science. Because the magnet creates a magnetic field, when it goes through the tube, the magnetic field repels the magnet upwards. Now, the field isn't perfect, so the magnet doesn't come to a stop, but still, it slows down from a fall to a nice, graceful drop. Take a look from above. Pretty amazing, right? Magnets. Not magic, science. The shape of something makes a big difference in how strong it is. Get some toilet paper rolls and put them in a square, and then stack books on top of them. They can hold weight. Thing is, they can actually hold a lot more weight than you probably think. In fact, the amount of weight just paper in a tube can hold is really kind of impressive. Ha-ha! And now, let's max it out. Building a door in a wall is hard, because how do you make a big gaping hole in your wall without your wall falling over? Well, people have come up with lots of ways to put doors and windows in walls made of stone blocks over the centuries. And you can do this at home with books like I'm doing or with building blocks. Just go up until you're happy with the height and then stack each next layer a little closer to the middle until the final layer touches just like this. And then you take a big heavy book and you drop it right on top. And it's pretty stable, and you've just made a doorway. It works even better if it's part of a wall because you want extra weight on the outside of these books here. So of course, I had to build one that was part of a whole wall. This is the same corbelled arch built out of little building blocks. And as you can see, I went closer and closer together until it meets at the top, and it is very strong. Whoa. Ha-ha! Now, let's max it out. Time for a mini-max. Here's how you can use the forces of things spinning around to defy gravity. Well, sort of. Take a ping pong ball and put it in a plastic container like a cup, or this is the top of a CD spindle. Put it in and start spinning it around. If you do it right, you can get the ball spinning only on the sides of your container and not touching the bottom. That's centripetal force at work. Oh. It works a lot better and is much more impressive if you have something that doesn't have a bottom. Fortunately, I do. This bucket doesn't have a bottom. Put the ping pong ball in the bucket and spin it around, and if I'm very careful, I can lift the bucket into the air and ta-da! I'm defying the force of gravity. Science!
Help, I'm being crushed by all this pressure. A whole kilogram is being pushed down on every square centimeter of my body. 103 kilopascals.
Actually, 1 kilogram for every square centimeter on your body is the exact kind of pressure that you and I are under at all times every day. We don't notice it because we're used to it, but it sounds like a lot, doesn't it? Well, it is. Here's an experiment you can do with a plastic bottle. Say at room temperature, there are 10 million air molecules in here. Doesn't really matter how many, but we'll say there's 10 million at normal room temperature. What happens if I heat up the air inside this bottle? This is warm water. What I'm trying to do is heat up the air inside the bottle because the air molecules, when they get hotter, move faster and need more room. So the 10 million air molecules are starting to escape out the mouth of the bottle and reducing the number of air molecules inside. And now I take the bottle out and cap it. Because the air molecules heated up and speeded up, they needed more room. Now there's less of them in the bottle. There's about 4 million air molecules inside this bottle, but they're all hot air molecules and they have a higher pressure, and you don't notice it because the air out here isn't crushing the bottle. But watch what happens if I cool the air inside the bottle. This is ice water. So what's happening now is the molecules are slowing down and they need less space. So they need less room and they're being crushed by the pressure on the outside of the bottle. Ha-ha! It has been crushed because the colder air molecules don't need the same kind of room as the hot air molecules. The room temperature air has crushed the bottle. The air inside has a lower pressure than the air outside. Pretty amazing.
Our maxed out mousetrap boat isn't the only way to give a boat propulsion. Let's look at another way using a balloon. Let's make a balloon-powered boat. All you need for that is something to be your boat and a balloon. Then you attach them together. Actually, the best way to do it is use a straw and attach the balloon to the straw using an elastic band. And then you attach it to your boat using more elastic bands, just like this. I've put a nice tape top on the boat to make it look awesome. And I also put a little bit of a riser here using just anything plastic to keep the straw nice and straight, because the question is, will our balloon-powered boat work better if it's pushing in the air or if it's pushing in the water? Well, let's do a science experiment and find out. First version, in the air. Oh, almost all the way. Now let's try it with the straw like this so it pushes into the water. Whoa, works so much better. Why? Because water is denser than air. The air coming out of the straw has to push against something to make the boat move. Water has more mass than air, so pushing against water has a better result. This is a pendulum. It's a weight that swings. It swings back and forth. Pendulums are pretty simple. It swings back and forth. Predicting the path of a pendulum, pretty simple. It's gonna swing back and forth. But wait, as I make it so much more complex by adding a pendulum. Now I've got a pendulum down here, and that one swings back and forth, and I've got a pendulum up here that swings back and forth. What will happen to this part of the pendulum when I let it go? Can you predict? Let's find out. This is a double pendulum, and predicting the path of a double pendulum is really difficult. It's still simple physics, but because there's a moving part attached to a moving part, it makes it way more complex. So, the question is, can we max it out even more? Of course we can. These are chaos pendulums. This one's a lever, and it's got another lever on the end. Whoa, and this one here is a perfectly balanced lever, and it's got a pendulum on either side. Whoa. Scientists and engineers have always said that the more moving parts something has, the more complex they are. Science. This is a chain of beads, and this is glass. Now, if I was to drop the chain of beads, what will happen? It will fall. Yes, that's right. It'll fall because of gravity. But watch this. This side goes up. Why? Because of gravity. Wait a minute. Why does one side go up because of gravity? Well, it gets a little complicated, but I can explain. But I think I'll have to put the beads back in the glass. Okay, so what's going on? Well, when this part of the chain starts falling out, it gets longer and longer, and it has more mass than this side of the chain. And if it has more mass, then it has more inertia. And when it starts yanking out very hard, this side of the chain gets yanked up out of the glass very quickly. And when it gets yanked up hard, it flies into the air. But then, of course, the direction has to change, so it goes around a curve and then goes back down. Because of the speed that it's going, that curve starts lifting up over the top of the glass. And that's how it works. There's a big difference in energy because this chain falls far. I try it from here, and it doesn't work as well. Why? Because the drop from here to here isn't as big. You want lots of force acting on the falling chain, which means the higher you do it from, the better it works. So maybe we should max it out. Yeah. But wait, we should wait for it to stop.